Hi, good evening, everyone. Hello, am I audible?
Yes, sir, but your voice is feeble.
Is it fine now?
Okay, kind of.
Sir, your voice is very low.
Yes, sir. Can you check your microphone?
Are you guys using earphones or what?
I think voice is okay. I think we can take.
Now is better. Now is better.
Okay. And if it is not, then please use the earphones because it's like in my laptop the setting is kind of all the it is full everywhere. Okay, so I think we are in week 6. I think this is the first session after your quiz, right?
Yes, sir.
Mm.
Sir, one small query, sir. In the discourse also we put
Mm.
one of the questions, 0 1 error loss is 0.5 and the square mean error loss is 1.25.
Uh,
But one of the options was wrong.
yeah, I think the marks is given to that. So I don't know whether that it is updated into your system or not. But
Okay,
from our side, when we check that, right, like calculations,
right.
the final evaluation when we did, we have given the marks to like only option. I think B and D was correct. So the it should
Yes,
be
sir.
better than that loss.
Got it, sir.
So the
Thank you.
marks are given accordingly. So it is not those who have written A and D. Possibly it is zero for them.
Got
I
it.
think, I think in the score checker it is yet to be updated, right?
Yeah. So it will update. It will get updated. No issues with that. Um, but I think I wrote one post on discourse, I guess,
Yes, yes. You have mentioned. You have mentioned. Yes.
regarding that. Like all three questions were there, and I given that for these questions
Yes.
the marks will
Correct.
be allotted. I think whatever the correct options are there.
Sir, in the orthogonal columns, the one which was not orthogonal columns,
Hmm.
if we'll get full marks for that, no, sir? It's only one correct option.
Yes. Yeah. So those who have written only one correct option, they get full marks.
Got it,
Apart
sir.
from that, if any other combinations, it's because those columns are not like the basis, right? Basis is not orthogonal.
Yes, sir. It's not
Uh,
orthogonal.
Actually, that is the correct basis for that set, I think.
Yes,
Uh,
sir.
and but the basis is not orthogonal. That's true.
Got
So
it.
I think there were like I think only answer key issues were there when we saw those, right? So I think we have corrected it from our end, but that will not reflect into your answer key, right? Because that answer key is already downloaded and like I think it is with you. So those changes will not be there in your answer key, but marks has been awarded, and I think I've post discourse on discourse also regarding like what all changes are there. Okay.
Sir,
Huh.
what about that option where they were talking about eigenvectors with the eigenvalue 1 minus I root 2?
See, I think that is correct one, but let me again go through it, right? So, see, it's not like okay. I understand if you think about that technicality and all, right? So, but if you just see that these are the pure real numbers, those are not like if you think that okay, root minus root two can be written as root two plus zero I or something, right? But that doesn't make sense basically. But let me see whether we can do anything about it. But from our end, I think that there were the mistake in answer key for three questions, and I think that has been addressed. For this question, let me think once more. Otherwise, most probably it will not change.
Okay, sir. Thank you, sir.
Yeah. Okay, so I think we are in week 6, right? And I think diagonalization part has been covered in last week. So okay, on an average, what do you think about the question paper? How was it? Were you able to solve that question paper?
Yes, sir. I would say, but I would say the construction of the paper, the questions were decent.
Uh,
But some generally, when you have multi-select questions, no, sir,
ah,
multiple of them will be correct. And if only one is correct, then we'll sit there and we'll keep thinking,
yeah.
did I make a mistake or not? So I feel few of those small things
Hmm.
had issues, but in general, it was decent.
Okay.
I think it was a bit lengthy.
on the lengthier part.
Yes, sir. Time also, I didn't get enough time to
Right.
finish it, sir. It
Okay.
was a bit too lengthy.
Because in case, if there is a mistake and, and 2 to 3 questions are linked,
Hmm.
then we'll have to go back again and,
But number of questions were less only, right? I
Sir,
don't.
but
the
each
number.
question took a lot of time to solve.
Which
Yes.
one? Okay, which all questions did you feel that the time?
Sir, one of the linear regression question was there, no, sir. It's a very lengthy question. I
Which one?
didn't have time to do it. I just guessed and ended up getting wrong.
That's squared error.
Regression one is
Squared
It was
error.
very lengthy, sir, the regression one.
No, which one? I don't know.
Linear regression, linear approximation.
Linear
Prox.
approximation.
So
Linear.
even the first question was so lengthy, like it took 10 minutes to solve.
Yes,
in
sir.
which
The
they-
questions, lot of calculation and all.
Yeah.
I didn't get time, sir. For the other exams, I reduced my time because of ML.
Yeah.
I okay.
So actually, because in one of the sessions, like I think the TA also solved in one of the TA sessions.
Okay.
What is the value of the attribute for this field?
I think
We
someone
need
is
to
speaking.
fetch that data in SQL query, right? But shall we do
Yes.
Yeah. So actually, in one of the I think it was TA session or a mentorship session. I can't recall exactly.
Mm-hmm.
But when we solved, like when the TA solved,
Yeah.
it took quite a lot of time, sir. Actually, because even we could see that like almost close to 2 hours. Though he thought that it could have been done in 1 hour,
Hmm.
but he took close to 2 hours. Actually while solving that, like
Is
it was.
No, it was not that lengthy, right? So I don't know.
Sir, it was very lengthy, sir.
It
was
was
very lengthy.
I thought it anyways, but
I spent 1.5 hours in the examination doing that, and I
yeah,
finished one
even
hour.
me actually.
The same.
I
Very lengthy, sir.
I spent almost 1.5 hours, close to 1 hour 20 to 25 minutes.
I also spent 1.5 hours. Still, I only solved 11 questions. I was not able to solve 2 questions.
Okay.
I was lucky enough that I had only one paper. In case I had 2 papers, I probably I would have had to spend only 20 to 25 minutes in the other paper.
Okay. Got it. Yeah. Okay.
So,
Let's see. Like maybe we can reduce the time in the interview.
because there is no information
because
about
the exam situation scenario is also different.
Ayush, I think there is some noise coming in from your end. Probably your another video is going on, right? So maybe, yeah, please, yeah, stop that and continue. Okay. Okay. So I think let's move on then. Right. I think.
Sir,
Uh,
even I also felt the paper.
I have seen that result is quite good only. I think few of the students have got like 100 marks as well. I guess 90 to 100 that bracket is there. Result is decent. Like I feel. Anyway, I think those who have solved the problems, they have done it well. Almost.
Sir, today is week 6.
Today is week 6, right? So before going into this week 6, there is one little concept. I think it's there. There are 2 3 concepts I wanted to address here. Maybe I think whatever remains, right, I'll take it into the Saturday session, solve with us. We'll keep it like 2 hour session here today. This, I think it's like after quiz 1, it is like the first question, first session. Whatever the doubts and everything will be there, the questions and all will solve on Saturday. Is that fine? Anyway, I'll be taking that session too, so we can continue where we have left it. So yeah, so before starting this part, right? Yes.
Sir, a person with one paper will get 1.5 hour time, and a person with uh, two papers will get only 2 hours. So, what's the meaning of it?
So see, the thing is, whenever
Is it
you go, no. See, I'll tell you what it exactly is. So in TCS paper, right? So whenever you go the TCS environment, any
fair?
question papers, right? So they conduct like most of the exams throughout the country, right? So the thing is with them is I think the uh, that button to submit the paper, right? So submit
Hmm.
button that will enable after 1.5 hours, right? So before that, nobody can leave the exam hall. It's the thing.
Sir, Kiran query is the one with the one paper gets more
Yeah, that's
amount
what
of time.
that's what I'm trying to explain.
Shyam, you got like
No,
more
see, wait. Actually, I had one paper because the thing is that in BDM we don't have quiz one, but in quiz two it would be same for me.
Yeah, but this is I think somewhat unfair because
Yes.
when we have two exams, then after 2 hours, exam will automatically be submitted.
exhaustion is taking
So
place, na?
yeah,
Okay,
there should be
I don't know.
some.
See, I think there is some with like okay, maybe I'll look
Sir,
into
actually, the
so,
problem is maybe if I say something, I don't know if it is fair or not.
huh.
We should not be seeing we should not be competing with others. I should focus on my grades and how I can manage. I mean,
No.
That is okay. No, it
We
is
are
not
able
about the
to
grades. Okay, I'll understand. I think let me intervene in this.
See,
Okay,
the thing is that the system itself is like that.
yeah,
If in case else, if else it should have been specified. If you are saying because this is a policy basically. Otherwise, it will go in policy level. Like it will simply say that 1 hour for one paper basically. The
yeah,
one
that
hour
is
is got
yeah. So
blocked.
there are generally it is like four
It will be
papers.
a very different scenario then.
See,
Then there is a lot of time constraint.
it is like very complex. I think
Yes,
from your side,
exactly.
it will feel like okay, I have only two papers, but if you think about that, those who are handling all of that, right? Like mostly the TCS will handle all of this. The thing is, we are actually saying that there are if anybody can have four courses, so ideally 1 hour each, right, for one course. So it will be like 4 hour exam, total 4 hour exam. So now in that, some of the students will have one question paper or one subject or one course, and some of them are having 2, 3, and 4. It's like varying, right? So
Sir, I think
and
one
with
paper they also get 1 hour only, na? I
let
think one
no no let
paper
me
is also getting 1 hour, na?
no, let me complete first. Okay, just listen to me, and then you can ask your queries. Okay, first of all, listen to me. It's like you are not listening to me and just bombarding the questions. And that is also see, it's my hunch. I'm not. I do not know exactly what is happening because I never have tried to understood that. But let me see again. If that is the issue, let me understand that and get back to you. But currently, what I feel is there is that this button, right? The submit button, it will get enabled after 1.5 hours, right? Or maybe you can say that 1.5 hours, right? So those who have with only one course, right, they also have to go from this let's say center after 1.5 hours only, right? So if they enable that 1 hour there itself, and I think see he is having two courses here, so I think that if somebody is having two courses, it's there on that hall ticket. I think by default he got like 2 hours of that timing or something like that, and there are those students with 2 hours of two courses, and they will get 2 hours of time, and after 1.5 hours, right? Anybody can leave, right? If you wanted to leave at 1.5 hours or you wanted to leave after 2 hours, that's up to you. So I think they have that kind of strategy. The first button will enable, the submit button will enable at 1.5. So those who have entered, right, they can continuously write till 1.5 hours. Another thing, I think it is like this. Somebody like I think we allow the students to enter into the exam hall 30 minutes, I think, late, right? So let's say if the exam starts at 2, uh, the the time to allow any student to enter into this exam hall is I think 2:30, correct? And now again, see, maybe that is also the calculation in mind that at least 1 hour they should get, right, to complete this paper or something like that. So for different kind of students, enabling these systems, right, I think that is little bit tricky. It's not like they haven't thought about it, but I think it is like that now they are settled with this. But let me check again with them like how these things works. Maybe probably I'll try to address that part uh, more concretely, right now I'm just whatever I'm saying is I can see from outside point of view it's like this only. Yeah, now you can tell me. Yes.
Sir, one more thing, sir. Week 5, the last part, sir, diagonalization of Hermitian matrices.
Ah.
I tried to understand and I watched recorded lectures. I wasn't able to, catch the concepts of that, sir. The
Okay.
diagonalization of Hermitian matrices.
Okay, so diagonalization of Hermitian, right? Basically, if you think about the diagonalization of Hermitian, right, they are diagonalizable. Uh, uh, if you know the properties, so A equal to A star, when we say it is a Hermitian matrix, right?
Yes, sir.
And another property of Hermitian matrix is they have the real eigenvalues, right?
Yes, sir.
Correct. And when we call any matrix to be diagonalizable, any real or complex, any matrix is diagonalizable when.
Sir, a matrix is diagonalizable when diagonal matrix is equal to S inverse into A S.
No, that is okay. That is like a kind of a definition, right?
Independent eigenvectors.
It should
Yes.
have, yeah, it
Independent
should have
eigenvectors.
n.
Yes.
If
Or
if A is
equivalently different eigenvalues, unique eigenvalues.
independent eigenvector, right? So I think, see, if this is the true, right? If you remember, I think if A equal to A transpose is like it's a symmetric matrix, right? So
Yes,
there
sir.
are the property of symmetric matrix are kind of similar to the properties of Hermitian matrix actually. So generally the symmetric matrices, right, they are diagonalizable. Okay.
Okay, sir.
Similarly, these Hermitian matrices are also diagonalizable. The thing here is these Hermitian matrices, right? They will have basically unique eigenvalues.
Okay.
Again, real eigenvalues they will have. Again, they will also have the unique eigenvalues, and hence you will end up into getting different eigenvectors.
Got it, sir.
So it
Sir,
is, yeah.
sorry to interrupt, sir.
Yes,
In the lecture, there was a process. He was trying to prove if an upper triangular, every matrix is similar to an upper triangular matrix. I didn't understand that at all, sir. How does that work? Like,
Okay, is it not covered into the sessions, like any of the sessions there? There is a Schur's theorem, there is a
yes,
spectral
sir.
theorem.
It's covered, sir, but I couldn't understand, sir.
You couldn't understand that
If
part.
you could, at the end of the lecture, could you please
Fine, fine.
help me out, sir?
Okay,
Thank you.
it's kind of similar to that. Okay, maybe I'll talk to you about. First of all, you'll need to understand what is similar matrix, right?
Yes,
And
sir. Yes.
probably you'll get to know that what is that similar matrix. Okay, maybe I'll talk about it at the end. Schur's theorem and spectral theorem. Maybe.
Thank you, sir. Thank you, sir.
Okay. Yeah.
Sir, I was not saying for anyone to personally, but I haven't taken one subject for exam, so I didn't know about it. But what happens when we enter in the exam? So if we have uh, two subjects for the exam, so after 2 hours or auto after 2 hours the question paper auto submit, and I didn't know about it. If a person get, I think that he or she is getting 1 hour and then auto submitted the exam, so I didn't know about it. That's why I said that it's unfair.
It's okay. It's okay. Let me check also. Is it how its system
No,
works?
no, actually,
Yes, sir. And if we enter in the exam late, then that time is deducted in the exam also.
Yeah.
no, actually, yeah, just wanted to say that no issues. The thing is that actually people like who have taken up MLF and BDM, so BDM they don't have quiz one, so that's why they got the entire 2 hours for MLF. Else,
Yeah,
it would have been the same for us also. So
that,
because we did quiz one, so that's why we got that extra
But
time.
let us say somebody has taken one course. What happens at that time? Do you have any idea?
In that one course time, because the thing is that actually they divide it slot to slot. If you can see, they don't divide it like, this subject is for this time.
Correct.
They will say mention afternoon slot 2 to 4. Say for example, 2 subjects are there. Any 2 subjects can be there. Student can have 2 subjects. So basically the thing is like that. If someone has 3 subjects, then definitely, because 3 subjects, like if someone has 4 subjects, I think 2 in the morning and maybe 2 in the afternoon, something like that. I'm not sure about that. I don't know.
But what about one course? Only one course. They can't.
I have one course. I got 2 hours.
That's
Yes, yes,
only one
2
course.
hours. Only one course. If
Only
someone has
one.
taken,
Only
yeah,
one.
and
I have 2 hours. I got 2 hours.
See, that's what, like, see, what is the issue? I think it is here. I think they the staggering process, right? Like when to cut off and all. I think it is bit difficult for them also. It is what I understand. Let me see. See, that's what. Like, let me see if somebody can maybe message me into the G chat, or maybe in the you can write an email to me. Maybe I'll check tomorrow with the team. I never
This
have
is
understood
even,
it.
sir, this is even not following the UGC policies as well. As if they are not competing, like we are getting 1 hour and somebody getting 2 hour for a per subject. So this is even not, guidelines are not even though followed by
but
them also.
no, buddy. The thing is that IIT is an institute of eminence, so they can make their own policies themselves. They don't have to follow the guidelines. So
You
that
just
is an autonomy which is given to IITs and NITs.
UGC doesn't work for us, that is
UGC doesn't work for. Even I am from an NIT. I am a pass out of 2009. That's why I am saying this to you.
no, it doesn't work. So the thing is, rules are all the rules, right? They are defined by IITs. Again, see,
That's
we
why
have one IIT law also, but still,
But is that rule okay to everybody?
no. See, the thing is, there is like, okay, committee of IITs also is there, but still, every IIT have their own. They can
they have
actually.
their own autonomy. Autonomy is there, so they
So
can.
it's just like, it is not about like UGC guidelines following on. That is a different thing. Okay, so don't worry about that. Don't go into that much in details, because it will not work anyway. See, what we can do is, let us try to understand that, and if anything is happening like that, can we have a solution to that? We can think about it. Okay, so it's like, if you try to say that, okay, these are the rules and all, I think that will not work anyway. Fine.
So I have given one paper earlier. I had 3 papers, 2 in morning shift, and I think one paper only in morning shift. Then I have only 1.5 hours.
Okay.
But one of my friends said this time he got 2 hours. I was also surprised how he got 2 hours.
Let me see. No, I also see, that's what I'm saying. I didn't have looked into that, because see, that is like different team who conduct the exams. Okay, I generally have don't I have the access to go
Let's
there and
continue to
ask.
the week.
Yeah,
So let's continue to the week.
yeah, let's we will see this now, and then I'll get back to that operational related issues. We'll deal later. Okay, okay. So I think the important concept here. So we are going to see the SVD. What is SVD is? It's singular value decomposition. I think it is one of the you can say that dimensionality reduction technique, possibly, or you. This is like one of the unsupervised learning process, right? I can think of it as, mostly it is a dimensionality reduction technique. One more dimensionality reduction technique we are going to see next week is PCA, which is principal component analysis. So these two processes are there. First of all, in this week we'll try to understand about SVD, which is a singular value decomposition. Okay, there is a concept called positive definite matrix. We'll have to learn about it. Before that, before going forward, I wanted to ask you about one more concept which is there. It is called as a Gram-Schmidt theorem. Have you learned about it? Do you have any idea about it?
Yes, sir. In Math 2, we learned, but
No.
could you give a quick
Not in MLF?
in MLF, I doubt if we learned it, sir. In Math 2, we learned Gram-Schmidt process.
Okay,
When we have to normalize some data, we use Gram-Schmidt.
Yeah, so I think yeah, so that is there. So I think this concept of Gram-Schmidt, right, is important while understanding singular value decomposition. So okay, let me go into details of what Gram-Schmidt method is there. I think that is one of the important topics again here. Before that, we'll understand about positive definite matrices. So okay, uh, and okay, there are like 2 3 maybe. So this is the core concept, which is called as a positive definite matrices. There are some other concepts which are like positive. Have you heard about this positive semi definite, positive definite?
Yes, sir.
Okay.
I heard this many times in the Gilberstein lecture, but I
Okay.
don't understand that.
Yeah, but not in the
I understood the SVD part, but I didn't understand what is this
okay.
positive definition.
So positive definite matrix, positive semi-definite matrix, there will be negative definite, and there is negative semi-definite. Okay. So these are all things are there. They are kind of, if you understand these two, you'll understand this two easily. So one of the core concept to understand here is positive definite matrix. I'll give you the definition of what it is and for which matrices it is applicable. Okay. So positive definiteness, or like whatever we are calling about here, right? Positive definiteness, positive semi-definite, uh, negative definite, and negative semi-definite. One of the important thing is the matrix has to be uh, sorry, the matrix has to be a symmetric matrix. Okay. I hope all of you know what is symmetric matrix means. So when you have A equal to A transpose, then we call it as a symmetric matrix, right? And what are the properties of the symmetric matrix?
Ej is equal to Aj.
Orthogonally diagonalizable, sir. Orthogonally diagonalizable.
That is there. Another, like, what about the elements? How they are actually placed? So
Diagonal will be different. It'll be a mirror image with respect to the diagonal.
correct.
Unique values will come in
Aj
the
is equal to Aj.
Right, correct. So this is A. So this is the symmetric matrix, right? Correct. So now this positive definiteness, positive semi-definiteness, negative definiteness, negative semi-definiteness, all these concepts are applicable only to which matrices?
Symmetric matrix.
Symmetric matrices. So if I say any square matrix is there, does it apply to that?
No, sir.
No. If I say any other like rectangular matrix, does it apply to that?
No, sir.
No.
So it will only applicable to the symmetric matrix. So there are few tests which are there to check whether the matrix is positive definite or not. So which are those tests?
Sir, do Hermitian matrices come in this because they're kind of
Yes, you can say that because it's the whatever concepts here are there, right? Mostly they are transferable to complex scenario as well, but that is not like in our scope of discussion here. So that's why I'm not going to dive into that. Fine.
okay.
Okay, so there are four tests through which we can say that whether the matrix is positive definite or not. So these are the tests for positive definite. By any chance, all of you understand what are the convex functions and convex functions, concave functions? Do you understand that? No?
Sir, no, sir.
Okay. Anyway, it is going to come into week 8, but I'll try to give you that maybe like gist of it. So, yes. So okay. So this kind of function, which is y equal to, let's say, x square, this is x, this y. This is called as a convex function. So there are few tests about it, like why it is called convex and all. But the important part to understand about it is there is only one minima, right? So this minima is called as a local minima as well as global minima. I hope you heard about that, right? Like y is equal to x square. How to find out its minimum value or global minimum, local minima? Have you heard about it?
Yes, sir.
Hard but not remembered.
Yeah. What are the tests to understand that?
F double dash kuch.
So let's say f of x. This is f of x. F of x is equal to x square. What do you do? The first condition is to set this equal to 0, right? To get the critical points or stationary points.
Yes, sir.
And what is so for this function? Let's say x square. It will be 2x equal to 0. That means x equal to 0 will be. So basically, you can get this when you have this, right? Correct. So it should when x is equals to 0 means what? Like I think I'm doing that mistake here. How it should be? It should be like this, right? Should go through. Is that correct?
Yes, sir.
All right. So in this case, and then what you do? F double dash of x, which is 2. If it is greater than 0, you say that it is a
Minima.
And okay, this is about okay. And when you have such kind of functions, right? Okay, I'm there are a few more definitions to it, but I'm just for intuition purpose, I'm just drawing some other. So let's say the function is like this. Okay, so how many minimum values are here?
3, sir.
3,
One.
right? One is here, other here, and
Global minimum is 1.
so this is a global minimum, right? Correct? And these are all local minima, right? So this is local minima, this is local minima, this is global minima, right? So, yes.
I can't get why this calculus part coming here.
I'll connect it. Like, don't worry about it. I'll at the end of
What's
this
the
slide,
use of?
you'll connect it. I'll connect where it is going to be used. I'll tell you where exactly it is going to be used. So when I talk about Gram-Schmidt theorem also, that also I'll connect at the end of this lecture. Fine. Is that okay? At least see these basic things you should know. So this kind of function is called as a convex function, right? Where you have only, so the global minima is equal to local minima. Fine. It does not have any other minimum values than this. So when the global minima is equal to local minima, that is your convex function.
So the left hand side one is not a convex function.
This is not a convex function. So
Okay.
there are tests actually. So you will have to pick 2 points and you'll have to check. So we have that in week 8 that all of this, but for intuition purpose, try to understand that whenever you have a global minima is equal to local minima, then you should say that it is a convex function. So this is not a convex function. Okay. Right. Okay. And there is another function, and when we say concave is like this. So what? The global maxima is equal to local maxima. Fine. Is that okay? This function is called as a concave function.
So it should be symmetric around the principal axis, right?
Yeah. So
it is necessary.
depends upon what kind of function it is. So suppose when I say y equal to x square, right? If I say y equal to x square plus 2, where that will be, so that will be, so then this is not going to be this will be the right?
Sir, y is equal to x cube has its minima will be minus infinity. Is that a convex function? I'm assuming not.
No,
it is not. No, sir.
No. Fine. Is that okay? So it depends on like what kind of function you are actually using. It depends on that. But try to understand at this point, at this moment, that this is called as convex function. Why it is important, I'll let you know. Because that is very important for understanding what is the difference between the positive definiteness and maybe positive semi-definiteness. Okay. What about this function? Let's say some function is like this. What about this?
Yes, sir.
It is also kind of convex function, right?
So is that a line in the bottom?
Yes, yes. So you can, okay, maybe if I can change the color, do that. Draw. Let's say this is kind of a function. Fine. Is it this is kind of a function. What happens here is, so all of these are the minima, right? And they are equal, like kind of equal, right? Is that fine?
Yes, sir.
Yes, sir.
Right. One more part about it is, let's say if you think of this, so what is the minimum value here?
0, sir.
Minimum is 0, right? Okay. What about this? It's not a convex. This is also not a convex, let's say, but
No, sir.
huh?
No, sir.
Okay, this is not convex. But what about this part? This is not convex, but what is the minimum value here to this function?
0, sir.
0.
And does all this have the you know?
This is also can be na, because minimum, maximum is also same.
No, the thing about this is, so there are actually when you understand about the convex function, right? It is like you pick 2 points, right? In that, and let's say if you pick these 2 points, suppose, and if you try to find a line, right, it should not cut the graph anywhere. Uh, if it cuts right, then that is not qualified to be a convex function.
So, sir, it should not cut the graph twice, no, sir?
Yeah, twice. Yeah, more than once. Fine.
Okay.
So in this case, this is not a convex function, but the point here is still it will have the minimum value as the same minimum value, and all the values are above that minimum value, right? If you think about that, all the values here, they are above that value. Fine. Okay, you just have to understand this part only. Not much details are required here. Now I'm going to write down all the tests which are there for positive definiteness of the matrix. So what is positive definite?
So it should be one-to-one function.
Yes. So what are the tests here?
Sir, but the y is equal to x square is not 1-to-1, no, sir?
Y is equal to x square is what? Yeah, 1-to-1 is what do you call about 1-to-1 as? When you say that it is 1-to-1 function?
Sir, if you draw horizontal line, it won't intersect.
Yeah, so that means exactly it will have for each of the x value, it will have only one corresponding y value.
Yes, sir.
Y equal to x square will fail the horizontal line.
So x is equals to 2 and x is equals to -2, it will qualify for that, right?
Yes.
Okay.
Sir, I have a doubt.
Yes.
Sir, in this case, is it possible in 3D case? In case of 3D, what you call curves, is it possible to have like one function?
3D case in the sense, I can you just explain it a little.
Like in this example of this concave or convex graphs. So if I take a point, so and I try to draw a line or something, so will it not cut the graph?
No. No, in 3D also,
Into more than
if the shape is kind of a bold structure, right, like this, so you can think of 3D, no, for this case. Okay, I think x square plus y square equals to, I think, z square. I think, will that qualify here for 3D case? If you think of I don't know, sense or not, but okay. So how it will look like? It will be a bowl-like structure. So for example, if I try to draw it here, it will be kind of like this, the kind of a cone, right? So it will again, you'll have the only one minimum value, right? The equation of cone, right, in this case, that will qualify for this. So this is a convex function. Fine. So upward paraboloid, for example. So let's say you are having a parabola, upward parabola in 2D case. If you have the upward paraboloid, let's say, and that will also have only one minimum value, correct?
Sir, it's actually not about how many points it is passing through. Like
There
the
is
line segment, Oh yeah.
yeah, convex function is like this. Okay, so suppose this is right. So this is a convex function because if you pick or this is okay, rather it will not be. But I'll try to see. This is like there are technical things here about the convex function, but it will take much time, right? I wanted to explain it in anyway week 8, but let us say uh, if I choose this structure, fine. So if I pick these 2 points, right, and if I try to, uh, let's say here, if I pick these 2 points, and if I try to get that line segment here, all the points on that line, they should be inside this, you know, graph, right? And if I pick these 2 points, you see that these are the points which are not on the graph, right, or which are not included into that figure. So in that case, this function is called as a is not a convex function. The convex function will be this function, the circle, right? You pick any 2 points in this circle, and it will be like it will not intersect the graph anywhere. Okay, that is one thing. Like, but the actual definition to it is like this. So there are 4 definition to this. One is called epigraph of f and all, but I think that is not necessary here. So I
Understood, sir. Understood.
Right. So here, if you pick any 2 points, right, and you try and get this line, the function's value, right? Let's say I wanted to find out the function's value at this point. It should be so actual function's value is where? In this case, actual function's value here, right? And okay, there is like there is one inequality also holds there, but it is called Jensen's inequality. But it is like that the function's value at this point, or rather, this is, let's say if it is f of a and if f of b, then and let's say this is a and b point on x-axis. So then, and this is a plus b by 2, right? Or a plus b by let's say I'll take the middle of this point. So then in this case, the function's value at a plus b by 2 point should be less than or equal to f of a plus f of b by 2. So this is actual definition for what? Convex function. You understand this point? Do you understand this point? So individual f of a, f of b, we do the interpolation between these two, and you pick any point on, like, let's say this a and b are the values on x-axis. You pick any point from there, and you just try to find out its function's value, right? That point's function's value. So a plus b by 2 is one of the points between a and b. So this interval a and b, you take any point between this interval a and b, you find out its function's value. This function's value should be less than or equal to the function's value at a and the function's value of b by that factor. So it's like here it is 2. Basically, it is lambda a plus 1 minus lambda b. And then this will be like less than or equal to. See, don't worry about it if you don't understand it here. I don't need that concept here right now, but I'm just giving the intuition. Those who understood, it's fine. If not, we'll see later.
So this is one of the key requirement for a convex function, right?
Yeah. So this is called as a Jensen's inequality. If you are interested, you can check it out. Otherwise, I'll anyway explain it in proper details when we see in week 8. Okay.
Sir, it should form some chord of an arc or tangent to it. Right?
What is
it? That means should form some chord of an arc on the graph for the tangent. It should become a tangent. Right? So that is when the line segment between any 2 points will be above or on the graph.
Okay, I didn't understand properly. But
so that is the definition given in the Wikipedia.
I don't know.
He's telling whatever you're telling, sir. Even I googled it. The definition, whatever you're telling, same thing.
So there are actually 4 definitions to it. Okay, this is one of the definitions. One is another epigraph and all. But okay, don't worry about it. See, it's there in week 8. If you are really interested, right, you can watch Wicked lectures. So they are there on YouTube. So Professor Arun has like explained it beautifully, so you can watch it there. But okay, let us move to this year. No, that is not important.
Sir,
Right? Yeah, tell me.
I'm saying because you said it should not pass through 2 points.
It's okay. It's okay.
So that is not the actual question.
We will discuss weekend. Otherwise, it will not get finished, right? This is week 6.
Yeah.
Okay. So I said the matrix has to be what? A symmetric matrix, right? For any symmetric matrix, it qualifies as a positive definite matrix. There are 4 tests. I said one test is eigenvalue test. Another test is determinant test. And there is another test. Third test is called as the pivot test, or you'll have to say that the pivot should be positive. Okay, and the fourth test is or I can say that this is what that equation gives me, that shape which I said, right? The upward parabola shape. X transpose Ax should be greater than 0. So I'll explain it one by one. Eigenvalue test, it says if all the eigenvalues, right? So if it is a 2 cross 2 matrix, how many eigenvalues does it have?
2, sir.
2, right? So all the eigenvalues should be strictly greater than 0. They shouldn't be 0, they should be strictly greater than 0. Then it is called as a positive definite matrix. Fine. There is a determinant test, which is like, okay, what are the determinants? So you'll have to break down this matrix into, like, now this is a 2 cross 2 matrix, so I can break down it like this. So this is the first part of it. What is the determinant of this? A. So A should be greater than 0, and then we'll have to consider entire this matrix. In this case, what will be determinant to this matrix? AC minus
B square.
AC minus B square is greater
than 0. So you listen to this. This is like strictly greater than 0, right? It is not greater than or equal to 0. It is strictly greater than 0.
Sir, if it's a 3 cos 3, the upper left corner should be greater than 0, no, sir?
So 3 cross 3 will look like this, no? Let's say A, B, and C. Okay, A, B, C, let's say, and here it is D and E and F. So here it is B, C, and F, right? It's going to be a symmetric matrix, right? So what will be the determinants to this? In this case, what should eigenvalue test should follow? Here lambda 1 greater than 0, lambda 2 should be greater than 0, and lambda 3 should be greater than 0. So if you remember the properties of determinants, the determinant should be equal to what?
Oh, they should all be real, sir.
Product of eigenvalues, right?
Yes, sir. Product of
eigenvalues. You remember that part?
Yes, sir.
So when I say that all the eigenvalues should be strictly greater than 0, if none of the eigenvalues is 0, then that means the determinant should not be equal to 0. Right? And in this case, the determinant will be defined by like this. So first determinant will be A should be greater than 0, right? So that means this first value has to be greater than 0. What about this? Then the second one is
B square minus D will be 0, greater than 0.
Minus B square will be greater than 0, right? And the third will be what?
Whole determinant.
Right? So that whatever it said,
D.
A matrix, let's say, should be greater than 0. So that these 3 are the tests for this. So see, all of these tests are there. You need to check only one of the tests, right? If that passes, most probably, not most probably, it will always be like, you don't need to check like all the tests, but there are the tests. Any test you can check for, right?
Sir, if any of the tests fails, then we can tell it's not.
Yeah, definitely it is not there, right?
So the second one, that determinant test, A greater than 0, and then what your AC minus, what is that?
This is the entire 2 cross 2 matrix, right? AC minus B square. How will you define this?
Okay.
Okay.
For this 3 by 3 matrix, I'm sorry, I missed out. Can you just explain once, if you don't mind?
Okay.
In short.
Yeah. Okay. So it's like, okay, I just rubbed it up. Fine, I'll do that again. So it will same things will follow for 3x3 matrix. That is like the only thing is it will have
Lambda
three lambdas,
Lambda
right? So it will
Correct.
be, this should be greater than 0. Again, this also it will follow. The only thing is, let's say if this is a matrix like this, no, A, B, C, and suppose the diagonal elements are D and E, and here it is F. So here it will be B, here it will be C and F, right?
Okay.
So matrix. So what will be the this determinant? So first is A is greater than 0, right? Is fine. What about this?
Correct.
So AD
AD
minus
minus
greater
greater than 0.
and
Correct.
then later on whatever the entire matrix determinant, which is like
Okay.
it will be A of D minus F square.
Understood. The entire determinant will be greater than 0.
It should be greater than 0. So the strictness condition is will have to follow for positive definite matrix. Is that okay?
This are pivot.
Pivots I will talk about.
Sir,
So,
I have a query regarding this, sir.
Yeah.
Yes, sir. Thank you, sir. Sir, in this in the lecture, sir, sir had given an equation that was ax square minus 2
Yeah, I'm coming to it.
bxy.
Don't worry about it. I'm coming to that part also.
In that equation, so regarding this, sir, AC minus b square, I have a query. So in relation to that equation, so they said that AC minus b square should be greater than 0, right, sir? My point is, can we take this as a situation also that the sum of A and C should be greater than 2b?
Greater than 2.
Only sum of A, S, and C should be greater than 2b, because they said A should be greater than 0, C should be greater than 0. Then they said AC minus b square should be greater than 0.
Okay. So
Because
what conclusion it says?
But that if you take 5 and minus 2,
there's an example,
5
sir,
plus
I
minus
would like to give, sir.
it is greater than
There's
0.
an example I would like to share. Like he gave an example of x square minus 10xy plus b square, y square.
No. No. What, from where it is coming? I don't understand it. You are saying something
From the lecture, sir.
No, I haven't seen lectures for like lot of long time, so I don't.
Sure. So I'll just
tell me.
I'll just begin from the first, sir. So in the lecture, sir had discussed about equation which says ax square minus 2bxy or plus 2bxy and plus y square is an equation. Okay.
Okay.
Ax square plus 2bxy plus cy square is an equation. And then he gave an example that suppose there is a condition that defies such this determinant test or this a square minus b square, or he said if x square plus minus 10xy plus y square is there, no? So that does not fit in this the positive definite that situation. So there he mentioned that AC minus b square should be greater than 0. So my point is can we also say that a plus sum of a plus c from that equation should be greater than 2b?
A and C you can interpret here like a determinant part. A is greater than 0. If C is less than or equal to 0, it will AC will be less than B square. Then it will be negative, like it will be less than 0. So that's why sir has told. And in that equation, positive definite equation should give positive value in every point, but it was not giving that positive value in every point, like 1 1.
Sir, the point is the determinant has to be positive, right? That is what you are saying?
Yeah.
So it
No,
is
see, I
simple,
think
right?
okay.
Why
I
you are
think
making complex?
yeah. See, okay. Whatever is there, let me finish all of that. See, I think you can connect with that again. Maybe I think whatever you're saying, I try to understand, and I think it is about this part actually. So I think whatever that x and y you are introducing right in here, I think it is that part. I don't know whether how you have interpreted it through there. I'll give you an example about it, fine, and then you'll got to know like what, or maybe you can connect it later on. Right now, I don't understand. You are saying that like a plus c should be what something. What equation you are saying? A plus C should be
ax square plus ax square plus
x.
2bxy plus
What is
cy.
x and y is there? Do you understand that part?
Sorry, sir, come again.
So what is ax and by or something square you are saying, right? This something
Ax square plus 2bxy plus cy square. It was in that.
that quadratic form, right?
Yes.
Let me come
Yes.
to that part. No, that's what I'm saying.
Okay.
Just wait
Okay.
for some time. I'll explain to you what is it means to be. Okay, I think you're jumping into that part right away, and then you're trying to communicate with this. Let us see we can connect it or not. Okay, what about the pivots? Pivots should be what? Pivots of what?
0 positive.
Yeah, they should be positive, but it is for a from a row echelon form, right? Once you go into that row echelon form, and then you'll only get the pivots, right? So first pivot in this case will be what? A, and that has to be 0. And what about the second pivot? It should be AC minus B square by A. So the determinant divided by A, and it has to be equal to 0. Is it fine?
Sir, how is the determinant divided by A the next pivot?
Okay. So if you okay, that will come anyway, but let me tell you how it will be. So this is your matrix A B B A. This is one, right? What is the row echelon form? What should you do? Let's say if this is a pivot, right? A is a pivot. Then what you do next is R2 changes to R, because you need to make this quantity as 0, right? So what will you do? R2 minus B by A times R1. Is that okay? Is that okay?
Yes, sir.
Yes, sir.
So what will be the matrix after this row operation? Is A, B. Here it is 0, right? What about
Yes,
this
sir.
part? It will be R2 will be C minus B upon A into B, right?
Yes, sir.
So that means C minus B square by A, and that is AC minus B square by A. If I do this, right? So it will be AC minus B square by A, and this is your row echelon form, right? And see this, and the next step will be what? It should be your pivot, right? Is that correct? So the first pivot is this, the second pivot is this. So both the pivots should be greater than 0. Okay? No issues, right? Till this part.
So the second part will be pivot only if the value is 1.
No. Pivot cannot be like the value should be 1, right? We can make it as 1, but before making it as 1, it can be any value, right?
If any diagonal matrix or matrix having any value in the second row, then we can consider it as pivot.
Yeah. Why not? We consider it, right? It is not necessary to have that pivot to be value as 1, correct, right? You make it to so that the equation will become simpler, or the otherwise it is not needed to have that value as 1. Okay, suppose this is a matrix 2 6 6 18, and that is this. I'm going to take that example also later on.
Sir,
But
make it the second one also be same, na? Then will be the symmetricity or
what is it?
18 should be 2 in the
Why?
example also.
Why?
Because
Symmetric
as it
diagonal elements shouldn't be the same, right? Only off diagonal elements has to be same, right? Let's say if this is matrix A, what is A transpose? It is 2 6 6 18. So A equal to A transpose. Then that matrix is symmetric.
yes, sir, just confused. Yes.
You shouldn't have this has to be 2, not required.
Yes.
Correct, right? So now in this case, I said it is, let's say 2 6 6 18. Now in this case, can you tell me what will be the first pivot? 2 is going to pivot, right?
Yes, sir.
And now what you do next? You will make it 6 as 0, so it will become 2 6 0
0.
right? So what are the pivots here? 2 and 0 are the pivots, right?
Yes, sir.
Yes, sir. Zero as pivot? No.
Sorry, not 0 as a pivot. Here you will have, okay, sorry. Here you will have
Zero pivot, sir.
yeah. So, it's not
Only 2 is a pivot.
2 is a pivot in this case. So 2 is greater than 0, right? But there is a like only one pivot is there, but there is no another pivot. So it is anyway no. So that will not qualify for our positive definite of the matrix, right? Because all the pivot has to be. And another part to understand here is how that will translate to your eigenvalue test, right? So when we say about 2 by 2 matrix, what we said?
It should have at least 2 eigenvalues.
2 eigenvalues, right? And no, and those eigenvalues has to be greater than 0. So if you think about this case, again, all things will maybe sum up to the same thing, right? So let's say determinant of A. What is the determinant of A? 0. So when you have determinant of A is 0, that means lambda 1 into lambda 2, that product is equal to 0. So this product will become equal to 0 when
One of the
either,
eigenvalues is
yeah,
0.
either one of the eigenvalues is 0 or both of the eigenvalues are 0, right?
Yes.
And if you think about this matrix, when after row reduction operation, we got this rank to be lesser than the 2, right? So that means it's a singular matrix, and if it is singular matrix, and one of the eigenvalues definitely will be 0, right? So then this matrix is positive definite or not?
No.
No.
So sir, it will. I have a query, sir.
Yeah.
So sir, this matrix will not even be considered to be that, or can it be considered to fit in the definition of positive?
This is not a positive definite. This is not a positive definite matrix. I will talk about this matrix, what it is, and we'll have to qualify, because see, we said that, right? There are 4 concepts related to this, which are those? One is positive definite, another is positive positive semi-definite, one is negative definite, and another is negative semi-definite. And all of these concepts are related to only which kind of matrices? Symmetric, right? Is that okay?
What is the fourth test, sir?
Fourth is I will talk about. So this matrix has to be qualified to it. So when it okay, this is another test which is called X transpose AX should be greater than 0. So what does that mean, right? Let us X is any unknown vector, or X is a vector of unknowns. Let's say I can write it as x1, x2, or since it is taken into the I think lectures, I'll take it as x and y. Okay, there are 2 variables x and y. If I multiply them, so if I do this, right, X transpose AX, right, then whatever. So if you think about this, right, it will form an equation. Okay, and that equation should be greater than 0. If that happens, then we can call it as a positive definite matrix.
Sir, that means the equation always has to be greater than 0.
Greater than 0, yes, because then only everything will follow. I will tell you about that. So let us say
What is A?
The matrix, the given matrix. So let us consider this matrix. Maybe I'll say that 220 6 6. Is that okay? Okay. If I wanted to do this matrix operations, what should I do? X transpose will be xy. This is 2 6 6 20. This is xy. Is that fine? Right?
Yes.
Okay. Can you tell me let's say if I do xy here, what about this? This is 2 by 2 matrix. This is 2 cross 1 vector. So the resultant will be a vector, right? 2 by 1 vector. So what that will be?
2x plus 6y and 6x plus 20.
This is 2x plus
2x
6
plus 6y, yeah.
Here it is
6x plus 20y.
Plus 20y.
Okay. And what will be the sorry. So what will be the final result here?
So it will be 2x square.
Okay, do you
With
think that this will be
12.
a single equation? Because this is one
This
cross.
will
Yes,
this will
sir.
have one row. It will have one row.
One cross.
Right?
One row, one column.
Yeah,
One.
so that will be x times 2x plus 6y plus y times 6x plus 20y. 20.
2x square
Sorry
plus
for
12xy
this.
plus 20y.
So it will be 2x square
2x square plus 12y
Plus
xy
6xy to
20y
20y square.
y square, right? And this will be then, can I say that it is 2x square plus 12xy and plus 20y square. So now this is what x transpose ax looks like, right? And we said that what is the test for this matrix to be positive definite? It is that x transpose ax should be greater than
Sir,
0.
does that mean for all x, comma for all y, this equation should be greater than 0?
Yes. So all real values, right? In this case, we will talk about real values. So all
So can y be 0? No? Y can be 0.
y can be 0.
Yes, sir. Here
But
it will be 0.
okay. So but both x and y cannot be 0, right? Okay. Only okay. This is there. So apart from x and y to be 0 for all values of x and y, if it can go to be it should be positive for any choice of pair, or like any choice you took pick for x and y apart from 0 0. See, if you pick 0 0, then anyway it's going to be 0, right?
Yes,
And
sir.
that is the single point. See, when I talk about that parabola part, if you remember, I said what? There is only one point where you'll get that 0, right? And that one point should be here, is when x is equals to 0 and y equal to 0. So for any other choice of x and y, it should not be 0. So if it is there, then what will happen then? You will find any other point here, right? Which will give me that 0 thing, correct, right? Apart from this, your a 0 0 point. So apart from this x equal to 0 and y equal to 0, can this be greater than 0, right?
Sir,
Okay.
so when you were teaching about convex convex function, sir, this
So-
function should be convex, sir.
This is convex function. Definitely, this is a convex function, right?
Okay.
But okay, so the importance about convex function there is like very different. Here it is not much needed, that the convex function. I just wanted to show that there is an upward parabola. So whenever there is an upward parabola, and when that will any equation, if that satisfies it, right, it will have only 0 when you have x equal to 0 and y equal to 0. Apart from any values of it, it shouldn't be 0, right? So that is like cup shaped, so inverted cup, right? Or maybe I don't know, inverted cup will be that convex function. Oh, sorry, concave one. But the cup, right? Basically, you will have that minima at one point. Okay. So how can I prove that whether this is going to be that part? So what I can do is I'll just take 2 common out of it. I will say that x square. So if I take 2 common, what will happen then? X square
6xy.
let me do like this way. Let's say x. Okay, I'll do one thing. Okay, maybe that also works, but fine. I'll do one thing and let me know whether this is okay or not. This is fine. Is this the same thing which is there above, or is it a different thing? Okay, what is the expansion of this term? X plus 3y square.
X square plus 6xy plus 9y square.
6y square, 6xy plus
9y square.
Times the 2 is how much?
Okay.
2x square plus
12y.
xy plus 9y square plus the remaining. So not 9, it will be 18, right? 2 times.
Yeah,
And
18.
2y square. So this will become what? 20y square. So is it the same thing which is there?
Correct.
Correct, na?
Yes, sir.
Right. So now you pick. Now if I can be able to write down this into this, so for any choice of x and y, you can take any negative, positive, like whatever the numbers are there, you can pick any point. So let's say if y is negative, this quantity will always be positive, right? Irrespective of y is negative or wrong. Correct? Is that correct?
Yes.
Why? Because it is a square, y square. So if you take minus y for any -2, -3, -5, -6, doesn't matter, right? It will always be positive. So if let's say if y is negative and x is positive, y is negative and x is positive, this quantity is positive. What about this quantity?
Always positive.
Always positive.
This is going to always positive. So both of them are always positive. That means greater than 0.
Right.
So can you say that if this kind of matrix is there, it will be always positive, right? If I have so if I take two unknowns and if I do this x transpose x, this will always give me the positive polynomial, let's say, right? Is that okay?
Yes, sir.
Okay, let us see another example, which is say 2, 6, 6 and 18, and let us try to do the experiment with this. What will happen? Let me know. So what is x transpose ax equal to what? Xy. Then a will be 2, 6, 6, 18, and this x and y. Okay. What will be the polynomial you'll get? So here xy. Here you will get, I think, 2x plus 6y, 6x plus 18y, and the final will be what? Let's say 2x square plus 12xy plus 18y square. Is that fine? Is that fine?
Yes, sir.
Yes, sir.
So what about it? Let's say x equal to 0 and y equal to 0. This is going to be 0, right? Apart from this, does it have any other value where it will be not equal to 0?
So we can take 2 common and try doing this completing the square thing, and if we get something similar, then definitely yes.
So this is going to be like this, right? Sorry, not y. Should be y. Is it fine? So that means you took any choice of x and y, you'll get 0, right? Sorry,
Yes.
you will not get 0.
Greater than 0, sir.
It will always be greater than 0.
Yes.
Okay. So okay. So let us take one more. I think but okay, one more thing is it is greater than or equal to 0, right? Okay, or greater than 0 rather, I can say, for any choice of it. But what about the other test? So what about this matrix 2, 6, 6, 20? What do you think about the let's say determinant? Let's say I'll try about the determinant test. What about this? What is the determinant of this matrix?
Greater than 0.
50 minus 30, which is 4, greater than 0. So that means it is definitely a positive definite. So if the determinant is greater than 0, what we can say about its eigenvalues? They're also
Greater than
Yes.
0.
they're also greater than 0. Okay.
The first 4 tests that you give, if any one test succeeds, then automatically all the other 3 sets have to
Yes,
have to
they
succeed.
have to. Yeah. So they are like complement to each other.
Got it.
Correct. What about this matrix? We are saying that okay, for any choice of x and y, we are able to get that greater than or equal to 0, greater than 0 thing. But what about it? What about the other test? Let's talk about.
Sir, we
First
can get
determinant is
zero.
first determinant is positive, right? What about the second?
Zero, sir.
Zero, na? Determinant is zero.
Yeah. So
Determinant is zero.
I said about determinants. How you should do it. Like we'll have to talk about all the determinants, right? A is
Okay,
greater than 0 and then x minus b square. So in that way, the whole determinant is actually 0, right? Because it is 18 into 2 minus 6 into 6, which is equal to 0. So what does that mean? One of the like let's say the whole determinant is 0. If that is equal to 0, what you can say about lambda 1 and lambda 2?
Greater than 0.
Not both, right? Like one of the eigenvalues has to be equal to 0, right?
One is zero.
So okay, I know what are the values here. So lambda 1 is equal to 20 and another values or lambda 2 is equal to 0 actually in this case. So this kind of matrix, right? It is called as a positive semi-definite matrix.
Sir, can you repeat that?
Sir, but for that matrix, we prove that it is not, but when we did the polynomial x transpose ax, it was coming correct only, no, sir?
Correct. Okay, now I'll write it down for you, like both things, right? All 4 tests. So what is the difference between this? I'll tell you. So positive, definite, and okay, just give me a minute. I'll need to plug in this charger. So I'll talk about positive, semi-definite. Okay, we'll talk about all the tests. First test is what? Let's say eigenvalue test. What is that eigenvalue test?
Greater than 0.
Lambda 1 is should be strictly greater than 0. Here it is like that. Here is that okay? I hope it is fine.
Yes, sir.
Yes, sir.
When I say greater than or equal to 0, that means one of the eigenvalues can be 0, right? So that strictness is relieved for positive semi-definite. What about the second
Both
test?
can be zero or not. And
Both can be
positive.
0. So, yeah, that is possible. But when you have both 0, what does that mean? Like that should be a 0 matrix, I guess, right?
Yes, sir.
Otherwise that is not possible, I guess. Then we'll
So
have,
zero matrix won't be positive definite, like semi-definite. Right?
yeah. So we don't have to. I think we are when we talk about it, it's like we are talking about this positive definiteness and all. It is for a symmetric matrix, right?
Sir, but a 0 matrix is symmetric.
Yes, but then what is the point of that matrix, right? Anyway.
So, sir, a 0 matrix, I think would be positive semi-definite, no, sir?
Actually, see, positive definite is kind of it's a subset of positive semi-definite. You can say that, right? So
Yes.
any positive
Lambda has to be greater than 0. Positive semi-definite. Lambda one eigenvalue should be greater than 0.
Semi-definite, see it like it's okay. The condition is either like they should be greater than or equal to 0. So one of the
Both-
eigenvalues has to be 0 in this case, actually. Positive semi-definite matrix.
Sir, but you just said it's a subset, sir. It might.
I'll tell you. I'll tell you how does this happen. So let's say this is my positive semi-definite one. Okay, this is a set of positive semi-definite matrices, and there is a subset of it. It's called as a positive definite. Is that fine? Because this thing, right? This will actually includes this also, right? If you are understanding the point,
both of them can be also 0. Both of them.
So both of them will be 0 when in which case 0 matrix. Then that is possible, right?
So then it would be positive semi-definite, no, sir?
Positive semi-definite, and actually that 0 matrix can actually said to be into that negative semi-definite also. Because see, it's on that line, right? See, don't worry about that corner case. See, you're just looking at that corner case, which is 0, 0 matrix. But apart from that, any other matrix, if you look at it, what does that mean? Is that this should include this, right? Is that correct?
Yes, sir.
Because when I say lambda 1 is greater than or equal to 0 and lambda 2 is greater than or equal to 0, this case also be considered, right, into this.
Right.
Yes,
Right.
sir. Yes.
So when I say that positive semi-definite, definitely every positive semi-definite matrix can be treated as what? Positive definite.
Yes.
Do you agree?
No,
Yes,
sir.
sir. With an
Why
extra
should
zero.
It's like
With the extra zeros.
one
Just extra
is
zero.
is
Otherwise,
is
it's
also
positive definite. No? Just zeros are extra. No? Otherwise, it's similar to positive definite.
So can I say that all positive definite matrices are the positive semi-definite matrices? Okay. Is it okay? Do you understand my statement, or
Yes,
okay?
sir.
Let me
Yes,
write it down. So let's say positive definite matrices are all positive definite matrices are positive semi-definite. Is this statement true or not?
yes, yes.
True. True, sir. True.
Sir, if one of them is 0
Huh.
and the other one is strictly greater than 0, then it
Huh.
would be positive semi-definite, no, sir?
Correct. Correct.
And assuming both of them are strictly greater than 0, then it is both positive definite and
Yes.
positive semi-definite.
Yeah.
Right, sir?
Yeah.
Okay, sir. Thank
Is
you.
that fine? So now this is positive semi-definite. This cannot be said to be positive definite. Why not? Because
Both.
for positive definite, it is that strictness is there.
Sir, sorry to
Yeah.
interfere. Just wanted to, because actually, like in the lecture,
Hmm.
like it was mentioned that for in case of positive semi-definite.
Hmm.
So, say for example, in case we are using the function like ax square plus 2bxy plus c
Hmm.
y square. So, in that case, sir, a is greater than 0, they have used, whereas the determinant is 0.
Where is the determinant 0?
Yes.
And that is okay, right? What
So,
is
in that case, definitely one, then sir, one of the,
eigenvalue should be 0, right?
yes, one of my eigenvalues will be greater than 0, another one will be 0, basically.
Correct. Right. That's fine.
Okay.
So, sir, if the determinant is 0,
Hmm.
then we can tell it is positive semi-definite. Is
Correct.
that a correct statement?
Correct.
Okay, sir.
But in that case also, we'll have to remember two things, which is what? So determinant test, when I talk about, right, what I said, A is good. So we'll have to check both these conditions.
Yes. A
A is
greater than 0 and
0 and
determinant 0.
AC minus B square is greater than 0. Here, in this case, positive semi-definite, A should be greater than 0. But
AC
AC minus B square can be equal to
Should
0.
be different.
Right? So this also has to follow. And if that is followed, does zero matrix come into this picture?
No.
Yes.
No.
No, right?
No.
Right, because one of the elements here we are saying that is not, that shouldn't be equal to 0, right? This A, I talk about.
Pivot
A.
element.
Is that fine?
So,
I hope this is okay for you. See, we'll have to move to the other part. So let me. But this is important. That's why I'm just spending some time over here. Then we can move to the next part. So what about the
in
pivots then?
semi-definite, there is also like a case where determinant can be 0.
No, that has to be 0. No, then only we can say. Or okay. Sorry. I think I have to mention it like this. Let us say. Sorry. Then it will be
If
like the correct one.
determinant can be 0, na?
Can be
That's
0.
me.
Yes. Because it has to include this part, no? Positive definiteness also it has to include. What about the pivots then? Here the pivots are like this.
Both.
By A greater than 0. Here by A can be greater than equal to 0, right? Is that okay?
yes, sir.
And what about fourth condition? Here it is x transpose AX, that polynomial should be greater than 0. What about this? X transpose AX is greater than or equal to 0. All right?
Yes, sir.
Yes, sir.
Yes.
Okay. So similarly, what can we say about the negative definite and negative semi-definite? Okay, just give me a minute. I'll just plug in the charger and then we can move forward. Okay? Is that okay?
Yes, sir.
Yes, sir.
Okay. 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 I'm sorry. One minute. I have to. Okay. All of you are here?
Sir, can you please go to page 5 for 2 minutes?
Okay. So all of you are not bored, right?
No, sir, we're here with you.
Okay, fine. Is it fine? Is okay?
Yes, sir. Yes, we were missing you, sir.
Okay. What doubt is here? Anyone is having any doubt here?
No, sir, I just wanted to jot it down.
Sure. Is it fine? Okay. We'll see some examples in the next session anyway about what this is positive semi-definite and all. We'll see those anyway. Okay. This is fine, right? Can we see for any 3x3 matrix? Shall we see any 3x3 matrix? Let us try. I'll take one example here, which is symmetric matrix, and maybe we can quickly see that how this will translate in here. All tests will see whether that will work or not.
Sir, from exam point of view, which of the 4 methods is the fastest?
I think, see, depends on which matrix you are solving, right? So most probably, I think the determinant test will be easier one, right?
Okay, sir.
Or in some cases, let's say any diagonal matrix is there, or upper triangular matrix is there, or lower triangular matrix is there. Which one will be good? What do you think?
So pivot one.
Determinant one, I think, will be good, right? Because no, determinant one will be good. Why? I'll tell you. Because any diagonal matrix or any upper triangular or lower triangular matrix, the eigenvalues are those which are what? The diagonal elements, right?
Yes.
But let us say, anyway, when we say about upper triangular matrix or lower triangular matrix, will that work here? No. Why? Because the matrix has to be a symmetric matrix. So any upper triangular or any lower triangular will not be a symmetric matrix. But any diagonal matrix can be a symmetric matrix. Definitely, right?
Yes, sir.
So in that case, diagonal matrix, you just need to see what are the determinant values. So for example, let's see quickly I'll talk about this. Let's say 1 0, what I said is 1 0 0 0 0 2 0 0 0 0 5 0 0 0 0 6. Right, in this case, if you wanted to find out the determinant of this matrix, right, do you need to find it out again? It will take a lot of time, maybe, or may not, but I think it's better to find out the eigenvalues. What are the eigenvalues of this? 1 2 5 and 6.
Yes, sir.
And all of them are positive. 6
Yes,
is
sir.
greater than 0. So does this matrix a positive definite matrix?
Yes.
Yes. Right, so that's how you should work. So sometimes you'll have to, like, whatever the whatever properties are there, you can use it and you'll get that answer easily, right? Okay, what about this matrix? Can anyone tell me determinants?
So 2 is greater than 0.
Determinant
4 plus 1 is greater than 0.
5. Okay, not 5, I think it should be 3. Right,
Sorry, sir. 4 minus 1, 3.
4
Yes.
minus 1 is 3. And then what about the remaining one? It's 4. Right, because that 0 1 is not required. We already have found out for 2 is like, okay, 4 minus 1, 3 to the 6, and minus 1, and I think it's minus 2. So it will be 4.
8.
4 4. Why it is 8?
No, I have done some mistake.
Minus
4. Okay,
plus
correct,
1.
correct. Sorry, I made a mistake.
Plus 1, right? And here it is like minus 2 and plus 0. So okay. So here it will be 2 into 3 6. 6 minus 2 equal to 4. Right?
Yes. Yes.
So okay, by this test, what does it qualify? It qualifies for positive definite, right? What about eigenvalue test? What are the eigenvalues?
1.
So here it is 2 will be eigenvalue. I think then 3 by 2 will be the eigenvalue, and 4 by 3 will be the eigenvalue. Okay, it is there. You can actually check it later on, but then you can think of it as these eigenvalues are also positive. Oh, sorry. Okay, not these are not eigenvalues. These are the pivots. Sorry.
These are not eigenvalues.
Pivots. The pivots.
Yes. Okay.
Because 2 is the first pivot. Another pivot will be this determinant, right? Divided by A. And here the last one is like this determinant by this one. Like you can actually multiply this and you just divide it by that. But what about the eigenvalues? Okay, I have this eigenvalues calculated, so I am just using them. There are 2 minus root 2 and 2 plus root 2. So all eigenvalues are also positive. Okay. What about its x transpose Ax? Okay, I'll write it down. What is it? You may check it later on. So what x should be here? It will be either x, y, z, or I can take x, y, z. Okay, let's say three variables I should take, right? Because we have 3 columns. So accordingly, I'll write it down. It is 2x square plus 2y square plus 2z square minus 2xy minus 2 yz. Is it going to be greater than 0 for any choice of x and y?
Yes, sir.
Yes.
Yes, right?
The other property satisfied, so this also has to satisfy.
So yeah, okay. Anyway, that will. But by looking at this equation, do you feel that it is going to satisfy? apart from x equal to y 0 and y equal to 0 and z equals to 0.
Yeah, we can convert it into a full square term, right?
You can think
If we
about
can
it.
convert it.
Yeah, it is possible. It is possible. So okay, you can think about it, and then you can find it out yourself. Fine. But now, okay.
It's always positive by looking at it also.
Okay, that's all. Okay, so that anyway is greater than equal to 0. That are the tests for you to decide whether this is positive definite or positive semi-definite matrix. This is okay. I'll talk about negative definite and negative semi-definite maybe after a while, or maybe by next session, because they are the same. What will change? What do you think? What will change here?
Less
This
than
will
0.
become less than 0. Yeah. So until now, whatever we have seen, right? So these are like upward parabolas, right? This for positive definite and positive semi-definite. For negative definite and negative semi-definite, they should be like this. So I'll talk about that maybe in the next session. For now, because I have to finish that SVD concept, right? At least we'll have to touch upon that. Otherwise, it will be not useful, right? Okay, so this is what we said about the positive definiteness or something, right? So it is only applicable to which kind of matrices?
Sir, square symmetric.
Symmetric matrix, right? Is that fine? Square symmetric or symmetric matrix. But let us say if I have any A, which is a M cross N rectangular matrix. So can we say any? Can we use these properties? Do you think these are the good properties to know for like any matrix? What do you think?
Sir, I think the pivot one, if we reduce it into row echelon, we might be able to use.
Okay, what else is there? Do you think that that how this A matrix, this M by N matrix, uh, can be converted into some other matrix such that it will give me? Is there any way? Think about. Okay, I'll give you the hint. Think about this A transpose. What we can do about that A and
Sir,
A transpose?
we can do in regression. We reduce the matrix into a rectangular into square. No, sir. Something.
Okay. No.
Multiply A transpose on both sides.
Sir, A transpose into A is symmetric, na? So
Correct.
probably we can.
A transpose A and A transpose, right?
A transpose.
So these both are the symmetric matrices. Do you agree?
Yes, sir.
So A transpose A, if this is M by N matrix, what are the dimensions of this matrix?
N cross N.
What about this?
M cross N.
Right? Is that fine? That is okay. And this will be a square matrices. This will be a symmetric matrices. And if they are symmetric matrix, I'll tell you one more property about them is they are positive definite. Okay. Can we check about like whether they are positive definite or not? How do you check that? So what we said about any matrix A is positive definite when X transpose AX should be greater than 0, right? If this satisfies, then I can say that it is a positive definite matrix. So let's talk about A transpose A. Suppose X, so this is A matrix. So X transpose A transpose A X, right? Is that okay? Correct.
Yes.
Can I write this as X transpose A transpose 1 and AX like this? So this quantity can be written as AX transpose AX, right?
Okay.
Huh? Is it okay?
Yes, sir.
And
Yes.
what is this? This quantity is a.
This is the norm of square of AX.
Right.
Yes.
So
Yes.
if this is this whatever the quantity is there, right? The square of it will always be what?
Positive.
So this will be a positive definite matrix, right?
Yes, sir.
Is that okay?
Yes, sir.
Right. And if so, that means I can show it for A transpose as well. Yeah.
We just go this lesser than 0. This will become negative
Yeah. So if this becomes, let's say, any sorry, x, okay, sorry, x transpose ax less than 0, right? That will become a negative definite matrix. Okay. We'll
All
talk.
signs related
Reverse,
to
reverse. What we have seen for positive definite and positive semi-definite. The reverse of that will be negative definite and negative semi-definite. Anyway, I'll make you that connection. But for now, we are interested into this positive definiteness of the matrix. Why it is that? Because our singular value decomposition is related to these two matrices. Which one? These two, A transpose and A transpose A and A transpose. Okay. Is that okay? Till now, is this fine?
Yes, sir.
Okay. Okay. No queries, right? This okay? This, we are fine.
yes.
Right? Okay. And see, if the matrix is positive definite, right, it will have all nice properties, right? So that means like we know that all the eigenvalues are greater than 0. We know that determinants are greater than 0. It is a, and what that translates to ranks. So if you have a positive, let's say if I say a matrix is a positive definite, what can we say about its rank?
So full rank.
Full rank matrix, right? Because its determinant is not, it's not a singular matrix, and if it is not, then it's a full rank matrix. So that means you will get uh, all n eigenvalues, right? If it is a
Yes.
n by n matrix, and then if you from there you can actually think about what will happen. Can it be diagonalizable? Can it be like all the things, right, which are there revolving around it? They will be uh, so all the properties will actually sync up if you understand that if the matrix is positive definite or not. Okay, right.
Yes, sir.
So I showed to you that any matrix is, let's say if A is a diagonalizable matrix, and in that case what we said is AS is equal to what? S lambda, right? Hmm? And what is lambda here? It's a
Uh,
diagonal
diagonal.
matrix.
Matrix.
What is the S matrix? It comprises
Uh,
of
Eigenvectors.
eigenvectors of A.
eigenvectors, right? Eigenvectors corresponding to
Eigenvalues of A.
n different. Let's say if I'm talking about A is a n by n matrix, because this diagonalization is applicable to only which kind of matrix is square,
Square.
right? It is not applicable to any rectangular matrix. So eigenvectors corresponding to n different eigenvalues, right? Or if they are same also, the eigenvectors should be what?
Distinct, linearly independent.
Independent, right?
Linearly independent vectors.
Dependent. That was the case when I saw when I talk about and if I wanted to reconstruct A, what? How will I reconstruct that A?
S inverse.
S inverse, right? So that means, can I say that A can be factorized into this, right? If I don't have any information about A, if I have only the information about let's say the eigenvalues of the matrix and the eigenvector corresponding eigenvectors, can I reconstruct A?
Yes.
Yes, sir.
Yes, right? Because
Yes.
the diagonal matrix, what are the diagonal entries in there?
Eigenvalues of A.
They were the eigenvalues of A, right? Fine. So
Yes.
diagonal matrix will have all the eigenvalues lambda 1, lambda 2, and like that lambda 3, and all are 0 here, right? That kind of diagonal matrix it is there. So if I have the information about the eigenvalues of a matrix and eigenvector of a matrix, I can reconstruct that matrix A, or or in another different way, I can say that A can be factorized into these three different matrices. Is that fine? One is
Yes, sir.
S. I can find out its inverse, and I have a diagonal matrix where all the diagonal entries are the eigenvalues uh, in that along the diagonal. And if I can actually factorize that A into three different matrices. So similar decomposition is there, which is called as a what? Singular value decomposition. Is that fine?
Sir, one small confirmation, sir.
Yeah.
S, the matrix S is the columns of the eigenvectors, no, sir?
Definitely, yes. All like all the eigenvectors arranged into the columns, and that
Okay, sir.
matrix will be your matrix S.
Oh, got it, sir.
Can you please draw the matrix?
Draw the matrix means like what do you want me to draw?
So could you please take an example?
Example.
We have seen, no? We okay.
Sir, could you do that at the end of the lecture? Even we'll get clarity. For now, can
No, I can show you that, but okay, let's quickly do into this. Suppose x1, x2, xn, x1, x2 up to xn are the eigenvectors. This is fine, right? In this way, is this okay? So x1
Yes,
is
sir.
some vector, right? They are all vectors. Is that okay? These are the eigenvectors corresponding to the eigenvalues. What? Lambda 1, lambda 2, and up to lambda n. Is that okay?
Yes, sir.
Fine. So if I wanted to write down AS, what my matrix A will be? Some matrix A. Okay, I don't know. Let's say that what kind of matrix is that, but A into what will be here? S matrix
X1,
x1.
X2.
So these vectors are arranged into the columns, so that this will be my S matrix. Is that okay?
Yes.
Okay. Do you remember the eigenequation? What is the eigenequation?
AX is equal to lambda.
Yes. So if I have, can I say that ax1 equal to lambda 1 x1? What does that mean? Corresponding to that eigenvector, lambda 1 is the
Eigenvalue.
So if you remember, whatever the a is here, what will be the multiplication of that will be? Can it be, so the first column will be like this, ax1.
Correct. X2.
Here it will be ax2,
Dot 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 X2.
right? So that is that okay?
Yes.
But if I use that eigenequation, what does that mean? Ax1 can I write down as lambda 1 x1?
Yes.
Is lambda
Yes.
2 x2? I'm not changing anything else here, right? I'm just using that whatever we know. Is that fine? Until this part is okay?
Yes, sir.
Now this matrix lambda 1 x1, lambda 2 x2, lambda n xn, can I write in this format? Like all the eigenvectors will be here. And now I have one matrix lambda 1, let's say 0, 0, 0. Here, let's say all is this. Just lambda 2. Okay, all are zeros, fine. Here also zeros and zeros everywhere. And here it is lambda n. Is that okay? So if you just do the multiplication of this with this, will I get this matrix?
So this would be X1 transpose, right?
No. X1. So just do the multiplication. Let's say, say you have
No. In ahead of lambda, sir. On the lambda side, I'm saying.
Where? Here.
No, yeah. In this one, X1, X2, dot 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 Xn, right? It has to be transposed, right, sir?
No. That's what I'm saying. Because I'm just post multiplying the lambda, right? If I
got it.
pre-multiplication,
Yes.
if I do the pre-multiplication, then I'll get that x1 transpose I need to is post multiplication. Is it okay?
Yeah, got it.
Fine. So what is this then? What about this? What is this? S? Your S matrix, and this is your
lambda,
capital lambda. So what I used to prove that AS equals to S lambda, right?
Same equation as earlier.
Right. No, I'm just proving it. Like I can reach to this expression. Right? This is the final expression. We have started with AS. So we are saying that there exists some S matrix, which is the matrix of what? Eigenvectors, right? Like all the eigenvectors of A, if I just multiplied that with A, what I'll get is I can be able to find out there exists one diagonal matrix which is denoted by let's say capital lambda, and all the diagonal elements will be what? The eigenvalues of that.
Yes.
And if I do that multiplication, that should give me that AS. So that means A is now diagonalizable.
Sir, in the orthogonally diagonalizable one, this S inverse will be equal to S. That is the only
Correct.
that's it.
Yeah. So in that case, I think we say generally A will be equal to then what? It will be S, this one, right?
Yes, sir.
So in that case, orthogonally diagonalizable, what will happen?
Is it? Yes, sir. Yes, sir.
I think in that case it will happen like this, right? S transpose, I guess.
Yes,
S transpose.
The S inverse is equal to only S transpose.
I think yes. In case of orthogonally diagonalizable. What do you mean by orthogonally diagonalizable? Leave about the diagonalization. Orthogonal means what? X1 transpose x2 should be equal to 0, right?
Yes.
Yes, sir.
Like perpendicular. So all the eigenvectors are actually perpendicular to each other.
Yes.
But these are like symmetric matrices.
Which one? No, it is not needed, right?
Okay, got it.
Huh? It's not needed, right?
Orthogonally diagonalizable, I got it, equal to 0. Yeah.
Okay, so that has to be there. And one more property related to this is also there. Let's say if my matrix is A square. So right, so let's say A was, I can be able to write A was like this, right? Or in other words, I can say that it is can I say that it is this is fine. Okay, A is equal to S inverse. What does that mean? Let's say if A is diagonalizable. Okay, when I say A is diagonalizable, then
A to the power k will also be diagonal.
Yeah. So this should be satisfied. What will happen then? What about A square?
S into diagonal matrix square.
So basically, what is A? A is this. So it is S
lambda square.
S inverse. Then here S inverse, right? So this S inverse into S. So I. So it will be S. Lambda is basically it's a scalar value, right? So it's a diagonal matrix, so it will become a square. So each of the diagonal entry will become square, and this will become S inverse. So what does that mean? A square is also diagonalizable. The only thing is all the diagonal values, right? So the eigenvectors remain the same, but the eigenvalues are what? The square root of it. And then that is again, so if any for A to the power k matrix, this I can show is that lambda to the power k inverse. Right? Okay. I hope this is okay.
Yes, sir.
Yeah.
Fine. Now let's talk about SVD. So the SVD is also a kind of a decomposition. That means I wanted to write A in terms of three different matrices, which are U, sigma, V transpose. Fine. This is called as a singular value decomposition of the matrix A. But what are A here? Do you know about that orthogonal decomposition?
No, sir.
No. Yeah. Okay, it's okay. So you know about this at least. Let's say S is A equal to S lambda S inverse. Is that fine? Okay, that is there.
Yes.
So now I am just proposing you a new term where I am saying that A is equal to U sigma V transpose. So what is U here? So U and V, they are what? I am just saying that these two are what? Orthogonal matrix. Okay. What do you mean by orthogonal matrix?
A into A transpose is equal to identity.
Right. So
A transpose A
should be equal to I. And I am saying that this sigma is a diagonal matrix. Okay. What are these diagonal matrix and all? I'll talk about later. But what was the problem with this matrix? This is what's good, right? Like I have already a decomposition for matrix A. Anyway, it was good. The problem with that is what?
It works only for square
It has
matrix.
to be for a square matrix. And only those square matrix for which inverse exists.
So this is only applicable to square matrix. This decomposition I cannot do for a rectangular matrix, right? But
Not
this,
even for those matrices.
yeah, but this SVD,
inverse.
yeah, SVD we can do it for any kind of matrix. It doesn't require to be what? A squared matrix. This is possible for any rectangular matrix. So this SVD is for any rectangular matrix, right? So this decomposition is for any rectangular matrix. This is for only the square matrix. What else is there? The eigenvectors. Do the eigenvectors need to be orthogonal? Not orthogonal, right?
Not necessary.
So if the eigenvectors are not orthogonal, what does that mean? They they are not independent of each other, right? Or okay, sorry, they are independent of each other, but the angle between them, right? So they are not like 90 degrees, but they are not perpendicular to each other. So, but in this case, in SVD case, they are perpendicular to each other. Let us talk about that. What this does, right? What does this SVD do? So SVD does is what it does, or is. Do you know the column space, null space, left null space, and
Yes,
I think
yes,
all
yes.
of you know, but do you know the relation between them?
The row space is perpendicular to
Yeah.
null
Row
space, and column space is perpendicular.
So the column space is perpendicular to the null space of a row.
No.
Null.
Yes.
Column space is perpendicular to the null of row space, and row is perpendicular to the null of column space.
Okay, let us say this is your row space. Fine. I'm saying that it is a row space. Then row space is perpendicular to what?
Null space of A.
Null space of row. Row is perpendicular.
Right. So row space of A is like basically column space of A transpose, right? Is that okay?
Yes.
And there is, let's say, there is one space. Why I'm like drawing like this? That is fine, right? Like I'm just wanted to show that it is span of the columns of that, right? And the angle between this and this is 90 degree here, correct? What about the column space of A?
Left null space.
Yeah, so it is perpendicular to
Left null.
I'm saying that okay. Just understand that okay, it's wrong, but it is. So can I say that it is null space of A transpose?
Yes, null space of A transpose.
So okay, and if A is any rectangular matrix, let's say A with m by n matrix, in that case, what are the dimensions of row space of matrix? Or can you say that okay, where that row space, in which dimensions it will lie to? Rm or Rn?
The null space, row space.
Rn, right?
Rn, yes.
All of you are okay?
Yes, sir.
Because it is A transpose, right? So basically, it will be in that. So it is kind of a column space of A transpose. So basically, it should be in what? Rn, right? I hope it is understandable because A transpose is n by m. So in that case, that column space, right? It will be in n dimensions. Anybody is having any issue with understanding this? If you
No, sir.
no, right? What about column space of A? It will be in Rm, right? That will be an Rm. So suppose there are two vectors. So till now we didn't have any connection between the vectors which are in row space and which are in column space. So let us try to think about it. Let us say there are two vectors here, which are what? Let us say the two orthogonal vectors are there. Let's say they are v1 and v2. in row space of A. Okay, let us say that is a orthogonal basis in row space. Is that okay? What I'm trying to say is this is V1 and V2 or span of, let's say, V1 and V2 is what? It's a orthogonal basis in what is it? Row space of A. Is that okay? Fine. These are the two vectors which are orthogonal in the or they form a orthogonal basis in row space of A. I need to find out the orthogonal basis by if I have this thing here. If I know that these two are the orthogonal basis in column row space of A, can I be able to find out the orthogonal basis in draw it properly? Say this is the space. Now you have, let's say, okay, I'll just draw like two vectors. Say U1 and U2. I need to find out, can by the information of this, if I have the orthogonal basis in row space of A, can I get the orthogonal basis in the column space of A? So SVD purpose is to what? To find orthogonal basis in column space of A for an orthogonal basis in row space of A. Is that okay? But how can you guarantee the orthogonal basis in row space of A? If, let's say, if you have the row space of A, and does it guarantee that it's a orthogonal? It will have an orthogonal basis. No,
You
right?
have to use the Gram-Schmidt. No?
Yeah. So you can make this orthogonal basis. If it is not there, we can make it as by using the Gram-Schmidt process. To so to make them the orthogonal basis if they are not initially, and by using this orthogonal basis in row space of A, I'll find out the orthogonal basis in column space of A by using what? SVD. Is that okay? Okay. So what are those vectors, right? So those are these vectors. So U1 basically is equal to A times V1 and U2 will become A times V2. But they might not be exactly equal to U1. So I'll have to multiply them with some constant, sigma 1 and sigma 2. I'll just tell about them what are the sigma 1 and sigma 2. So sigma 1 and sigma 2 are called as the singular values.
Sir, just wanted to interrupt.
Yes.
Sorry. Yeah, sir. So in this case, since you have used, like, can you just go up? Yeah. Since you have used here in this case, like sigma 1, sigma 2 U2 equal to A V2. So, or whatever, U2 is basically A by sigma 2 V2, right?
Correct.
So, like, it is some scalar form of V2. Okay, it's a transformation. Okay.
Transformation. It is a transformation.
Transformation. Okay.
Correct, right? Because we are multiplying with A, no?
Yes, got it.
Okay. Okay. So it is A times V1, it is A times V2. So when we are actually maybe expanding it or contracting it, and then you divide it by some constant or multiply with that, it doesn't matter, right? It's like then you do the scalar transformation there later on. But initially it is the transformation. Okay.
Time, like,
don't worry about it. It's like if you're not able to understand that part, it's fine. Don't worry about it. I'll just think of, so basically I'm just saying that A can be written as U sigma V transpose. We'll arrive it to that point first.
Sir, could you once again just explain?
Okay. So we have, let's say, okay, maybe without diagram I'll try to explain. Let's say you have V1 and V2. Okay, they are what? They are the orthogonal basis of what? Let's say column space of A transpose.
Yes,
Is
sir.
it okay?
Yes, sir.
Or can you say that in row space? They are in row space, or they are orthogonal basis in column space of A. What do you understand? Basis. You understand the basis, right?
Yes,
Yes,
sir.
sir.
Right. So basically, you have those vectors which actually you can actually use to get that space, right? Whatever the subspace is there, right? And by using this, right? Let's say I know that they are in column space of A transpose. So can I be able to and they are the orthogonal basis of matrix A. So with this information, can I get the orthogonal basis in? I wanted to find out what orthogonal basis in column space of A, right? Or column space. Is that okay?
Sir, so first we'll have a matrix A and we find the orthogonal basis of
Yes.
row space and column space.
Row space, and I don't need to find out actually the orthogonal basis in column space. I can find it out by using what? Let's say A times V1.
Okay, yes, sir.
That will be my U1, and U2 will be AV2. So this is your, but this is not exactly be the orthogonal basis. So you'll just multiply with some constants. So sigma 1 and sigma 2 are the constants. They are called as singular values.
Sir, one small doubt, sir. Why? How is this connected to the row space being perpendicular to null space and column space is perpendicular to left null
No,
space?
it is not. No. In general, we know that, right? We know that already. See, column space of A. No, it is not related. What I'm saying is, row space is perpendicular to that, right? Null space.
Yes,
of
sir. Yes, sir.
So we have, let's say, in row space you have this, right? These two vectors there.
Yes, sir.
I wanted that this kind of vectors. So when I say that orthogonal vectors, so can I get these two vectors in column space of A?
Yes, sir.
Right. This is like this we know. This is already there.
Yes, sir.
We need to just showcase that okay, these two are perpendicular spaces. These two are perpendicular spaces. But if
Okay.
I have the information of these two vectors into row space, can I have that similar? Can I translate that orthogonality, right? Basically, between the two vectors in the column space of A also. That is what we are interested in right now. Okay.
Okay, sir.
So now what are these singular values? These are basically square root of lambda 1 and square root of lambda 2. What is that? Lambda 1 and lambda 2? These are the eigenvalues. Values of A. Okay.
Sir, how is AV1 equal to sigma 1 U1?
Actually, okay. So it is not how, but it's like okay. That is the definition. Let's say.
Okay, sir.
Saying that like we said for this, right? This matrix S lambda is inverse.
Yes, sir.
When we say that A is diagonalizable, what does it mean? There exists some diagonal matrix lambda, right? Which
Yes,
I can actually find it out from any square matrix A,
Okay.
which have that kind of setup. So I am saying that this is possible if I have the span of two vectors which are like perpendicular to there, right? I can actually find out its similar kind of orthogonal basis into column space of A. That is what the information I am having. I am just saying that it is possible.
So, sir, here U1 and U2 are orthogonal basis for A.
A in column space of A.
In column space of A. Okay, sir.
You see that.
Sir, in this one you have taken A to be a square matrix or what, sir? In this one?
No, A can be any matrix.
Because you have mentioned, na sir, like can you just go down? No, yeah, you have mentioned, right, sir, eigenvalues of A. So to find out eigenvalues of A, it has to be a square matrix in a way, right, sir?
Okay, but sorry. Okay, they shouldn't be. Sorry, you're right. Okay, they are the eigenvalues, but not the matrix A. Basically, they are the eigenvalues of this A transpose.
Okay.
A transpose.
Okay.
Then it will be a square matrix.
Yeah, thanks for noticing. Yeah, sorry. This should be like eigenvalues of these matrices. Okay. So first of all, let me write down this first. So I'm just saying that A. So by the definition of it, what are V1, V2, we are up to, let's say, VR. Why I'm stopping at here? Maybe you can understand it. So any matrix A can be any matrix, right? M cross N matrix, and A times this, right, should be equal to what? U1, U2, up to, let's say, UR, and then sigma 1, sigma 2, up to where should I go? This is the diagonal matrix. What do you think? R, M, or N? R. Okay, and all the others are 0. Is that fine? Do you understand this part?
Sir, here you said that this is an orthogonal matrix. So here, if we take the the transpose
This
of
is
the,
orthogonal and this is orthogonal.
so they both are orthogonal.
Yes,
Okay, sir. Okay.
They both are. That you can see, right? Because they form a basis, right? Orthogonal basis. So V1, V2 are they form an orthogonal basis in row space. U1, U2 form orthogonal basis in
Okay.
column space.
So, another definition for an orthogonal matrix is the column vectors are all orthogonal to each other.
They are there, right? That is true, right? So okay, V1 and V2, they are the two vectors, right?
Right.
So can they satisfy this condition?
Yes, sir.
Yes.
Definitely.
U1 and U2 are this. So can they satisfy this condition?
Yes, sir.
Yes. And this is what this U1 and U2 and V1 and V2 we have taken that one to visualize, because we can only visualize in 2 dimensions. But let us say you have like V1, V2 to, let's say, V5, Vn, let's say VR. So, but all of them, right? V1 is perpendicular to V2, V1 is perpendicular to V3, V1 is perpendicular to, so each of the vector, right? They all are perpendicular. So they form a perpendicular basis. So perpendicular means like they form a orthogonal basis.
Got it.
Right. And similarly, U1, U2 and all, like whatever. So here, that's why I say is that this is orthogonal matrix. This also is a orthogonal matrix. Okay.
Okay, sir. Sir, and V1, V2, VR are the orthogonal bases for the column space, no, sir?
Orthogonal basis in column space of A transpose, right?
Sorry, A
so
transpose.
Row space, and this is orthogonal basis in column space of A, right?
Okay, sir. And sigma 1, sigma 2 to sigma r, those are the square root of the
eigenvalues, but which
eigenvalues of A transpose?
A transpose or A transpose A?
A transpose A.
Because you know that the eigenvalues of the symmetric matrices, right? A transpose A and A transpose, they should be same. The only problem is what? Let's say you have A as M cross N matrix. What about A transpose? The matrix size is?
Sir, M cross M.
And
A
what about A transpose A?
M by N.
And let us say M is greater than N.
Yes, sir.
In that case, okay, how many eigenvalues does it have?
M.
M eigenvalues. How many eigenvalues does it have?
N.
N. But when the M is greater than N, then there are M non-negative eigenvalues will be there.
Sir, how is that possible, sir?
I will tell you. Eigenvalues are there, and the remaining ones, right? N minus M. The eigenvalues will be 0.
0.
Sir, I did not understand.
Got it. Okay, no issues. I'll tell you how that is possible. See, it should be actually. So if you think about it clearly, right, then you'll get to know. Maybe I can take one example for that as well. But okay, so let's say if a 2 by 2 matrix is there, right? Sorry, 2 by 3 matrix is there in case. So its A transpose will be what?
2 into 2, sir.
And A transpose A will be
3 into 3.
3 into 3. So how many eigenvalues does this have?
2.
2. And how many it should have?
3.
3. When I say that the eigenvalues of A transpose and A transpose A are same or equal.
Yes, sir.
Do you agree that the eigenvalues of these two matrices should be equal?
Yes, sir. Yes.
You know
Symmetric
that.
matrices, both are symmetric matrices.
Symmetry matrices, right?
Yes, sir.
Let's say lambda 1 and lambda 2 are the eigenvalues for this matrix.
Yes, sir.
So, and lambda 1, lambda 2 and lambda 3 should be the eigenvalues for this matrix, right?
Yes, sir. So lambda 3 will be a repeating one, sir.
It shouldn't be repeating one, and that's why it should be equal to 0. So, so because we said that it should be equal, right? When they are equal, in that case, the trace of the matrix should also be equal, right?
Yes, sir.
Or another part is determinant should also be determinant. I think that will become 0 for this matrix, right? But trace of this matrix A transpose should be equal to trace of this A transpose A, and that is possible only when you have that lambda 1 and lambda 2, and again we are saying that lambda 1 plus lambda 2 is same as that of lambda 1 plus lambda 2 plus lambda 3, plus I am saying that lambda 1 and lambda 2 should be equal. If they are equal, right, in that case lambda 3 should be equal to 0.
Right, sir. Got it, sir.
Okay. So the discussion prior to this was what I said was
sir, one more thing, sir. How did you get A V1 is equal to U1? And how are they both?
No, A1 is not equal to.
Sorry, sigma U1.
U1, yeah.
How did you get this, sir? And how is V1 column space and U1 row space, sir? How?
Okay, so see, this is a decomposition, right? How? So, like for example, let's say when I said A is decomposed like this, so like S lambda S inverse, so this is a result, right?
Yes, sir.
So this is also a result, like singular value decomposition. It kind of says that there exists something like this.
Okay, sir.
Use me that, right? It's not like somebody has proved that, okay, let's say if I take the matrix like this, U matrix like this, or V matrix like this, I can actually show that it will follow this step, right? This is what it is like. There is no proof for that. Like, how can I show it to you that
it's an observation? Okay, sir, got it, sir.
Okay.
So, sir, the procedural method that will follow is, sir, we'll take the row space of A and use Gram-Schmidt process to find the
orthogonal basis. Right.
After that, what is next step is AV1 is equal to sigma 1 U1.
Yeah.
Like that will find all the U. Will find all U's.
Sure. I'll show you the
give an example and show, sir.
Yeah, numerical examples I'll show you like after this only, and then we'll close. So this is fine. AV I can write it as U sigma. Is that okay?
Yes, sir.
Okay. So what then? A can be written as what? U sigma V inverse, right? Okay.
Yes, sir.
But I said that V inverse is a orthogonal matrix, and U also is a orthogonal matrix. So I can write U sigma V transpose, because in that case V inverse should be equal to V transpose, right? In the orthogonal matrix condition.
Yes, sir.
Okay. Then what can we say about A transpose A matrix?
Symmetric matrix, sir.
Yeah, but by this, let's say if A is equal to U sigma V transpose, how will I write this? A transpose A.
V sigma transpose. Sigma U transpose.
Those and
U sigma V transpose.
Right.
Yes,
okay.
Sir.
And if that is the orthogonal matrix, then
identity.
It should be identity.
Yes, sir. Sigma square and V sigma square V transpose.
V sigma square and
sir.
V transpose. Yeah.
It should be V sigma transpose, right? V sigma transpose U transpose U.
It should be V sigma transpose.
In the second line, no?
On the left hand side, no sir, V sigma transpose U transpose, no sir.
Here.
Yeah, it is sigma transpose.
No,
Sigma
okay.
transpose
Okay.
U transpose.
Let us say A is what? U sigma V transpose, right? What
Correct.
about A
A
transpose? A transpose will be U sigma V transpose of transpose, right? Is that okay?
Correct.
So when I introduce transpose inside, it should be like this, no? V transpose will come this side, and it will be sigma, and then it will be U transpose, right?
Sir, I think it will be sigma transpose only, sir. But when we do sigma transpose into sigma again, then it'll become the norm square. So so it'll become a dot product, something like that.
That is okay. I'm just writing it as sigma square. So basically, it's like diagonal entry, right? It is sigma 2 like that 0, right? Or sigma r, and into sigma 1 to sigma r and all zeros. So it will be the square of that, right? So let's say it is a into a kind of, let's say, what will be the multiplication of this?
No, sir. When we take a transpose of a bracket thing, we flip it and we put transpose and everything, no, sir. So here sigma transpose also will be there, no, sir. Like for A, B whole transpose is
Okay.
No, he's correct. He's correct. See, the thing is that it will not change it because
Okay, what will
anyway
happen?
sigma is a diagonal matrix. That's
Okay,
why.
got it. Okay. You are saying that. Okay, I understand now. You are saying that it
Yeah.
should be sigma transpose. We sigma transpose is transpose.
Correct.
But if it is a diagonal matrix,
But it will not make any change.
transpose
That's
will
why
be
it
equal
will
to
stay.
sigma, right?
Yes, sir. Sorry. Yes, sir. Got
It will become sigma square only, basically.
Yes. I think in a flow I forgot to tell you that. Okay. But yeah, because any diagonal matrix, if you take a transpose of it, it will remain the same.
Yes.
Basically. And that is why I directly wrote it. Sorry for that. I just
And
then
also, the sigma transpose, sigma is not the norm we are getting. Sigma will have the same dimension as the original matrix here, right?
yeah. So it
If
will
it
be like
is m by n,
yeah. So it will
then
be like sigma
yeah.
square. So sigma 2 square, and it will be
If A is m by n matrix, then the sigma square will be some n by n matrix.
correct. That
It
is true.
won't be the norm.
So I'm just saying that it is let's say sigma r square and we transpose, right? Is that correct? Okay.
Sir, I have one more question. Sir, in the diagonal here in the right side, you put some of the sigmas as 0. Is that because m and n something, if it's a rectangular matrix, one will be greater than the other?
Where I will written 0? This thing?
No, right, sir. Just right to your cursor.
Here?
No, sir. Right to your cursor. Yes, sir. There, sir. Yes, sir.
No, it is a diagonal of diagonal elements, right?
Sir, no, sir. The diagonal elements, the last few ones you wrote as 0.
No. They should be sigma r. So sigma is basically this one. This sigma 1. What is it? Sigma 2 up to sigma r only.
Okay, sir. So proper diagonal matrix with everything else. Got it.
Yeah. So I'm not including that zeros there, right?
Got it, sir.
So what will happen here? So okay, if you think of this, right, is it similar to what do you say? Similar to that thing like A equal to S lambda or
yes,
nothing, right?
K is equal to S
Let's
lambda.
say it is K some matrix, and I can actually be able to find out. So V is the orthogonal basis, and what sigma square actually here, they are actually lambda ones, right? Lambda 1, lambda 2. So these are the eigenvalues of which matrix?
A, sir. A transpose.
So here, yeah. So these are the lambda 1, lambda 2, lambda r. These are the eigenvalues of what?
A transpose.
A transpose A. Fine.
Yes, sir.
But here the only difference is V is your orthogonal basis, right? That was not there when when we talked about this part. I hope you understand that part. Okay. And similarly, I can show for A transpose what it will be. U sigma V transpose. Then A transpose will be sorry, not V transpose. It is V sigma U transpose. This will become identity matrix, and it will be like U sigma square U transpose, right? And then again so in this way I can say that the sigma 1 sigma 2 sigma r, right, or sigma 1 square sigma 2 square sigma r square, they are also same for A transpose also. So that way I can say that the eigenvalues of A transpose A and A transpose are equal. Okay, is that fine? So if I say A equal to U sigma V transpose, in that case what is U? U is U is a matrix formed by eigenvectors of what?
A transpose.
A transpose. And V transpose is a matrix formed by eigenvectors of
A transpose.
and sigma is actually what? It contains all the singular values. Singular values basically they are the square root of eigenvalues, right, of any AI transpose or A transpose. Okay, I'll take a small example here. Maybe we can see more examples in the next session to understand this concept, like how we can do it. So this is your matrix A. Fine.
Sir, can you take a rectangular matrix, sir?
Yeah, if you want, I can take this. Okay, you can. Okay, then let's say I want to take what 1 0. Fine. Is that okay?
Yes.
Okay, but they are not fine. And what about now? What we talked about here is this, right? So first of all, what I need to find it out. Let's say we found out V. V first. And what is V here?
Eigenvectors of A transpose.
So what will be A transpose? It is 4 4 1 minus 3 3 0, and then what about A transpose? Sorry, A transpose A. It will be 4 minus 3 4 3 1 0, and then you'll have 4 4 1 minus 3 3 0. Okay, the dimensions of this matrix will be what? 2 cross 2, right? 2 cross 2 or 3 cross 3? 3 cross 3. So it will be 16 plus 9, 25. 16 minus 9, how much? 7. 4. Here it should be, I think, 4. Let's say 16 minus, oh no, not 4, 7. 16 minus 9, right? 7. What about this?
25, I think, sir.
5.
6%.
Here it will be
4, sir. I think 4 4.
4. What about this? It has to be
4.
4. It has to be 4 again, and the last one is 1. Is that okay? Right?
Yes, sir.
Okay. So can I find its eigenvalues? Okay. Before that, let me find it out. A transpose. What is A transpose? 4 4 1 minus 3 3 0. Here it will be 4 4 1 minus 3 3 0, and then I'll get a 2 by 2 matrix here, right? So it will be 16 plus 16 32, 32 plus 1 33,
33
and
0
here
0 18
0 0
0 18
plus 9 18. Okay, is that okay? So now I need to find out its eigenvalues and eigenvectors. Uh, Before finding it out, let us try to understand something here. So what are the dimensions exactly, right, in this case? So A equal to U sigma V transpose. What is the dimensions of A? Okay, sorry, not n by n. In this case, it is what? 2 by 3, 2 rows and 3 columns. Correct. This matrix will have dimensions as 2 by 2. This will have 3 by 3. Right. What about the dimension of sigma?
Same as the A, 2 by 3.
So 2 by 3, right? Then only this is possible, right? Then only this multiplication is possible. So 2 by 3 means what? It will have like this. So 1, 2, okay, 2 entries will be here and other entries has to be 0. So can you tell me how many eigenvalues does it have? Does it contain? Or
2.
Sigma 1 or 2, right? Yeah. Now let us solve for this because the eigenvalues will be easier to calculate in this case. What are the eigenvalues? Here
33 and 18.
So lambda 1 equal to 33, lambda 2 is equal to
18.
18. And then what will be the singular value here?
Root 33.
Root 18, right? So how this my sigma matrix will look like? 0, 0, 0, root 18, 0, right? Now, can you tell me the eigenvectors corresponding to this here? What will be the eigenvector corresponding to A transpose? So here you have lambda 1 equal to 33, lambda 2 equals to 18. So the eigenvectors corresponding to it will be
1, 0 and 0, 1.
1, 0 and 0. Right. That is what your matrix Q. Is that okay?
Did you like work this out? Or?
No, you can. Yeah, you can work it out, right? Like it's easy, right? So for lambda 1 equals to 33, the equation will be what? This matrix will be 0, 0 and 0. How much?
For diagonal matrix, eigenvectors will be.
It will be A transpose minus lambda. Sorry.
No. We need to find out the eigenvectors of this matrix, na? Okay. If you don't understand that, okay, let me do it. Okay. So lambda 1 equals to 33 and lambda 2 equals to 18, right? That you agree?
Yes, sir.
What is A transpose matrix? It is 33, 0, 0, 18. So let us call this matrix as K. So K minus lambda I, right, should be equal to 0, right? To find out the eigenvectors. Is that correct? I have already found out the eigenvalues. Sorry. Okay. No, not like this. Should be like this. K minus lambda I times the x equal to 0. And that x will be your eigenvector, right?
Right.
I hope it is okay. So basically it is 33 minus lambda 0,
Correct.
0, 18 minus lambda and times that x1, x2. Now I need to satisfy this thing. So for lambda equals to 33, it will be 0, 0, 0 minus how much? 20, 15 is equal to x1, x2 equal to 0, or basically 0, 0. So the equation I get it is 15 x2 equal to 0. That means I know for sure x2 equal to 0. So
1, 0.
t 0, right? And if I take t comma, it will be 1, 0. And what is orthogonal basis also? It is 1, 0 because length of it is 0. And for 18, what will happen? 18 you will get like here you will get 15. You will get 0.
Same
0.
reverse 0, 1.
So next 2 and 0, 0. And that case also I'll get the same the reverse vector 0, 1. Sorry, 1 0, 1, right? So finally, what are the?
How did you get that 0, 0 minus 15? That this one.
I plug in lambda equal to 33. So if I plug in lambda equals to 33 here, this is 0, right? 33 minus 33.
Okay, got it.
Okay, what about the second matrix? What is second matrix? Can anyone write this matrix or remember this at least? 25, 25, 1, 7, 4, 4. Okay. Can you tell me A transpose A, right? that is equal to 25. It was 25 here, it was 1 here, it was 7 here, it was 4 here, it was 4 here, it was 7 here, it was 4, 4, right? Now in this case, what I'll get. So again, I have, what are the lambda eigenvalues for this case? 33, 18 and 0, right?
Yes.
So for 33, this will be what? For lambda equal to 33. What I'll get here? 8 minus 8?
Minus 8. Minus 7, 4.
7, 4, 7.
Minus 8. 4, 4. Minus 32.
2. X1, X2, X3 equal to 0, 0, 0. What should I do next? Can I do the row operations and find it out? Maybe you can do, or is there any other way to solve this? Oh, I think, okay, I'll have to do it. Okay, I'll do it for one. Maybe you can do it for the remaining ones, right? What should I do? Let us do, I'll make it as 1. So it will be 7 by 8 minus 1 by 2, right? And then I'll subtract the 7 times. So R2 changes to R2 minus 7 times R1. So in that case, it will be minus 8 minus of plus like 49 by 8, right? So 64 minus 49 is how much?
15. Minus 15 by 8.
15. So minus 15 by 8. Here, 4 minus of
minus 24.
8.
Minus 24.
Minus 24. So I need to make it 0. In that case, R3 changes to what?
Sir, the third vector is just the linear combination of first two. And just make them 0.
How come?
The third row is just a linear combination of first two.
First two, huh? How is it possible?
If you just add them, no, you get -1, and 8. And then you multiply it with -4.
Right.
Correct.
So you can just make the last row zeros. And
yes, that also will be work it out. But okay, let me do it now. Now I have started it, so it's fine. Yeah, that is true. That is correct. But what you said is correct. So it is R3 minus 4 R1, right? So what I will get here? So it will be like 4 minus plus 28 by 8, right? Huh?
Yes.
50, I think 60,
it will be. 60 by 8.
60, huh? 60. What about it? 8. Minus 32 minus 16. Oh no, not minus 16. Oh, I think we have done the mistake here, right? It is like, it shouldn't be like R2 is 4 minus 7 times of this part, right?
Yeah.
It is 7 times 2, right? 15. Correct, right?
Correct.
15. Here it is 16 now. And what about
15 by 2, right, sir?
Huh?
15 by 2.
Is it?
4 plus 7 by 2, no, sir?
Okay. Yeah, 15 by 2, right? 15 by 2, right? What about this? Minus 32 minus there's a 4 times 2, right? So minus 64 plus 4 is 60 by 2 minus 30.
Sir, and this one will be 60 by 8, right?
Which one? This one, right? Yeah. 60 by 8, no? Right. So 60 by 8 is how much? I can
15 by 4.
30 by 4 or 15 by 2.
15 by 2.
Alright, let us keep it as 60 by 8, no? It is also not harm. or calculation, right? So here it is 15 by 2. Maybe I can use it in here. So it is 100 minus 7 by 8 minus half. This will be what? 8 as it is, 15 by 2. And how much I should add it here? 4 times, right?
Yeah. So you'll get 0, sir. Basically in the last.
Yeah, right. And then anyway, this has happened. I can make this as 1 also, but I'll let it be there. So here x1, x2, x3, that should be equal to 0. Now we are minus 15 by 8 x2 equal to yeah. So basically, what I did something. Okay, sorry. So it is minus 15 by 8 x2. I can say that it is 15 by x2 equal to 15 by 2 x3, right? And that I'll get 15 will get cancelled to 4. So I'll get what? X2 equal to 4 times x3. And from equation 1, I'll get x1 minus 7 by 8 x2 minus x3 by 2 equal to 0. So we'll have x1 as 7 by 8 times x2 plus x3 by 2, and then in terms of x3 it will be 4 times x2 is 4 times x3, so 7 by 2 x3 plus x3 by 2, so I'll get 4x3 again, right? Just check whether I did not do any mistake here. I think not.
Yes, sir. It is okay, sir.
Right. So in that case, my x3 can be any choice. Then
441 will be there.
441 will be there, and now I can actually make it into the normalized form, and what that will be. So 16 plus 16, 32, 33, right? So 4 by root 33, 4 by root 33, and 1 by root 33. So that is one of my vectors, and I think you'll get the similar vector here as well, which is divided by root 18. I think you should get it, or at least you should see all the vectors are orthogonal, right? So you'll get the similar values, I think, but you can.
Sir, so do we have to check for orthogonality?
No, it will automatically come in. Actually, you check it or not, you'll get it anyway. So what are U's? U is I think it was like this. I'll not do it for others, right? Okay, you can do it anyway. It's late for now. We can continue maybe in the next session. So here it was what? Minus the root 13 to 0, 0, 0, root 18, 0. And now you had one of the eigenvectors as what? Corresponding to this. What's this one? 4 by root 33. 4 by root 33. And I think 1 by root 33. For 0, 0, I think you can easily find it out anyway, I guess. You can think of this because you will have to find out this only x1, x2, and x3. 0. Okay, so we'll stop it here. I think I hope you understand how to solve this. Maybe if you get time, or if I get time, I'll just post it on the discourse, or any one of you can actually maybe note it down and post your answer to this question on discourse. So can you get this? If anybody is interested, please get this A, this matrix A, and solve that for SVD, right? Find out its singular value decomposition. If I'll get time, I'll just write down the expression there on discourse. I'll post it on there. Is that okay? There are few more topics I need to explain, that Gram-Schmidt method and all. Maybe we can talk about them in the next session. Along with that, we'll see the questions from, like numerical questions from positive definiteness, positive semi-definiteness, negative definiteness, and negative semi-definiteness. But I hope you understand at least what are these concepts, right? At least, or what are these terms as from today's session? That be okay?
Yeah, right, sir. This coming Saturday session, is it at 4 or?
I think I'll shift it to evening time.
Okay.
I think maybe 6 to 8 or 7 to 9. 6 to 8 is fine.
Sir, keep the same time throughout the rest of the course, na? That will not cause any confusion actually.
Okay.
Yes, sir. Could you tell us clearly, like next Saturday session, when will it be?
Okay, so maybe I'll talk to with another of my colleague is Shubham, and then we'll decide for throughout the term.
If it is evening, it is better, sir. I mean, I think.
No, I think why it is not kept in the evening is that I think there are few other courses whose sessions are clashing, and that was the schedule which we are following for like long time. But I don't see any of you are actually having the sessions at that time.
Sir, what about afternoon?
Afternoon session, I'll shift it to evening.
Huh?
Will that be okay?
Are there any afternoon sessions?
No.
There are none.
Sir, where will we be intimidated? Where will you intimate about the change of times?
No, it will be reflected into your calendar.
Oh, it'll change in the calendar. Okay, sir. Okay.
Yeah. Got it. Anyway, I am telling you in beforehand itself, like it will be from 6 to 8 or 7 to 9. So basically, I will try to keep it as 6 to 8 on Saturday.
Okay, sir. Sir, any other doubts we have, can we clear in the next session, sir? Is that
Sure. I think, I have to clarify you about the Gram-Smith method also. I'll
Okay.
show you how it will work, and then maybe we can connect all the concepts, right? Whatever are there together, the positive definiteness, all this Gram-Smith and all, and then we solve some problem in Solve With Us session. Is that okay?
Yes. Thank you, sir.
Okay.
Yes,
Thank
sir.
you, guys.
Thank you.
Thank you, sir.
Thank you so much, sir. Good night.